Check 1, 2, check, check. All right, welcome everyone. We're going to get started with the welcome and introduction, and then the first talk's not till 1:30, so there's time for people to filter in, take a break if you need something. Here's our code of conduct. As usual, please try to respect it, offer constructive feedback, share the air, value new ideas and encourage innovation, communicate context, show appreciation, acknowledge teamwork, and listen to understand. Okay. So we have a new co-chair. Frank Bryan was co-chair for 6 years. Is Frank here? I see him. He's enjoying his retirement, sort of. Yeah. And then I jumped on about 4 years ago following Baylor Fox Kemper. And now we have a new internal co-chair, which is Gustavo Marquez. Welcome, Gustavo. Took over on April 1st. Very glad to have him. I'm going to be moderating the session here before the break, and then Gustavo is going to take over after the break. So we're up at the top. Welcome, Code of Conduct, Logistics. As you can see, we have a nice slate of talks for you today. Usual deal, if you have questions at the end, please use the mic so the people online can hear you. And I believe there's been a cancellation after the break, but we've already worked it out. Somebody else is going to take that over. So we should be straight through. One comment is the last talk before break is going to then go into discussion, and the discussion may go a little bit into the break. But if you hear them calling for the photo, we'll step outside so we can be in the photo. We're not gonna have a photo with no ocean people in it. Okay. So Maheswar is our first speaker here. Is the first speaker online,
Yeah.
maybe?
Yes, I'm here.
Yeah.
Hopefully,
I
I'm
think he might
audible
be
also.
online. Do we have him? Working on it. Okay.
Yeah. Hello, everyone. So, am I audible?
And now we can see you.
Yeah. Okay. Thank you. Shall I start or what is it?
Screen.
Sorry, yeah. Your voice is actually breaking. I'm not getting the your voice.
We can hear you. Can you hear us?
Yes, yes. Now I can hear you.
Yeah. Now the audio is cutting out. We can't hear you.
Okay. So is it audible now? Yeah, whenever I am speaking, your voice is not coming. Okay, so just give a thumbs up if I'm ready to go. Yeah, thank you, thank you. So can I have the permission to share my screen? I don't have the permission right now. It's showing host is disabled participant screening setting.
Can you share your screen now?
Let me check. Yeah. Okay. So I think my slides are visible to all of you in the full screen mode. So I'm assuming it's going on well. So, hello everyone. My name is Maheshwar Pradhan, and I am from India and currently working at Indian Institute of Tropical Meteorology, Pune, India. And this presentation will be towards addressing the impacts of resolving diurnal cycle of the ocean on different scales of predictions. So, let me brief some of the challenges of using coupled model as a forecasting or a prediction tool. One such major challenge is to represent the diurnal cycle of convection over the ocean and the atmosphere. And there are several attempts to overcome such issues by modifying the cloud or convective parametrization schemes. Recently, Z et al. Has addressed such issues by revising the convective triggering function, and there are other attempts of modifying the cloud microphysics also towards improving the diurnal cycle of precipitation over the ocean as well as the over the atmosphere land part. And these studies have actually shown improvement in diurnal phase of the precipitation, but the improvements in diurnal amplitude of precipitation is still not significant. And there are other challenges at intraseasonal timescales, such as the intraseasonal phase and amplitude of MJO and monsoon intraseasonal oscillations over the Indian parts are not quite realistic. And on the other hand, there are suggestions that by improving the diurnal air-sea interaction or diurnal oceanic fluxes and sea surface temperature can be a way forward to address such issues. So how do we represent the air-sea interaction in a coupled model? So mostly the atmosphere and the ocean model talks to each other by passing surface heat fluxes, atmospheric model. So these are the boundary state or boundary conditions which representation can be improved throughout via different parametrization scheme. And one such attempt is carried out here by considering the CFS-P2 as our coupled modeling tool. And here in the default configuration, what is there is the ocean model forces the atmospheric model with the bulk SSTs. So bulk SSTs is basically the 5 meter or 10 meter temperature that the ocean model simulates, and the atmospheric model at the same time forces the oceanic model with the surface meteorological variable and surface heat fluxes. And in the modified configuration that I am calling it as sensitivity run, where the bulk SSTs are being corrected to the skin temperature through the help of QoED 3.0 algorithm. And at the same time, the atmospheric fluxes which were earlier present, those are being corrected. And now the QoED 3.0 flux scheme that is used to compute the surface fluxes, and those are passed on to the oceanic model. So basically, we are changing the atmospheric boundary condition as well as the oceanic boundary conditions on the go. And as we know, there are two processes. One is the diurnal warming, and other is diurnal cooling, which controls basically the diurnal cycle of ocean. And during the most of the seasonal factors, such as the solar insolation, wind, current, and cloud cover, that controls the diurnal warming. And in a like calm wind condition where the surface warming can go up to 3 degrees centigrade, in those conditions, the bulk temperature and the skin temperature are very much different. And in suppressed convective phase of interseasonal oscillations such as MGO and mesos, there will be the impact on the atmosphere will be much higher than as compared to the active spell. And similarly, the diurnal cooling, which is almost constant throughout the season, and it basically the nighttime cooling controls the diurnal cooling of the surface ocean. So in the control run, what I have presented in one of the earlier slides, so the control run doesn't have the diurnal cycle of the ocean, and it has the NCAR flux scheme, and the sensitivity run, what I presented, has the diurnal cycle, and it has the Quad 3.0 algorithm. Sorry. So here I present what is the impact of this modification of on the surface ocean. First, we have looked at the local solar time scale, the diurnal variability of the sea surface temperature. The blue line represents the mood buoy observation. The dashed line represents the control run, and the dotted line represents the sensitivity run. What we can see is that in absence of diurnal cycle of the ocean in the control run, the timing of minima as well as the maxima is delayed as compared to the observation which is in the blue line. But when we implement the diurnal cycle of the ocean, the timing of minima as well as the maxima coincides with observation, and this is a comparison over the Bay of Bengal, and similar comparison has also been made over the Pacific Ocean also. At the same time, what we calculate is the diurnal range of sea surface temperature over the tropical basins, and these are for during the boreal summer monsoon, boreal summer period. And what we can see in the observation, there is a very high diurnal range of sea surface temperature over the summer hemisphere, and the control run quite misses it, and the amplitude of diurnal range hardly restricted to 0.3 degrees centigrade. But with the modifications and implementation of diurnal cycle, what we can see, the sensitivity run quite reproduces the diurnal amplitude of sea surface temperature quite well, and the difference between the sensitivity and control run is as high as 0.5 degrees centigrade in the summer hemisphere. Similarly, we have also seen the impact on mixed layer depth, which I have not presented here. Directly, I am going on to the impact on the diurnal range of precipitation, and we calculate it by subtracting the minima from the maximum during a 24-hour cycle. What we can see in the observation, what we can see during the June to September period, there is a very high diurnal range in the precipitation over the equatorial Pacific Ocean and the Bay of Bengal, Indian landmass, and equatorial African landmass, and over the equatorial Indian Ocean also. But in the control run, the amplitude is again hardly restricted to 1 or 1.5 mm per hour, which is not realistic. The diurnal amplitude is underestimated in the control run, but in the sensitivity run, when we actually resolve the diurnal cycle of the surface ocean, that directly impacts the diurnal cycle in the precipitation also, and the amplitude of diurnal amplitude is also amplified. So previously, there are studies which relate the surface diurnal ocean to the atmospheric diurnal cycle. For example, like Clayton and Chain, they have actually used the atmospheric model, and they have shown the sensitivity of skin temperatures to the diurnal variation of the convection also. So going on to the intra-seasonal scale, so rectification is basically a process where your enhancement in or reduction in the diurnal cycle can directly impact the intra-seasonal variability, and we have quantified that in terms of by calculating a amplitude of rectification by this is intra-seasonal variability with the diurnal cycle minus intra-seasonal variability without the diurnal cycle divided by intra-seasonal variability uh, with the diurnal cycle. Sorry. And here we calculated the amplitude of rectification for sea surface temperature at the mood buoy locations throughout the tropical ocean. And in observation, what we can see over the Indo-Pacific one pool region, there is a the amplitude of rectification is as high as 10% in the observation, but in the control run, the amplitude of rectification is hardly restricted to or 2% or something. But in the sensitivity run, because of the presence of diurnal cycle in the ocean, the amplitude of rectification is amplified and it goes up to 6 or 8% in the Indo-Pacific whirlpool. Similarly, at some of the other locations where the amplitude of rectification is negative, that is also amplified in the sensitivity run. So next, going on to what is the impact of this SST rectification on some of the interseasonal variability, such as the monsoon interseasonal oscillation. Basically, monsoon interseasonal oscillations are the periodic oscillation of convective anomalies over the Indian Ocean and the Indian landmass, where it periodically oscillates between the active and break phase, where active phase is defined as the period where Indian landmass has a positive convective anomalies. And uh, previously, many studies have shown that most of the coupled model could not reproduce a stronger active phase followed by a break phase, so that we can see through a Hofmuller plot here. That is, the precipitation anomalies are averaged over the Bay of Bengal region, and the y-axis basically represents the days from the with respect to the active phase, like 0 coincides with the peak of the active phase, and it plus 10 days plus minus 20 days to plus 20 days to cycle we have plotted. And here on the y-axis we have the meridional extension of these anomalies, and the color contours basically represent the sea surface temperature anomalies, and the shadings are the precipitation anomalies. What we can see is that in the control run, the precipitation anomalies are quite weaker as compared to the observation. Similarly, sea surface temperature anomalies are also weaker in the control run. But and there are suggestions from by Lee et al. Where they have suggested that inclusion of skin temperature may resolve the problem of a weaker active phase followed by a break phase. And by implementing the skin temperature parametrization, what we can see the sensitivity run is the active phase is now stronger in terms of precipitation anomalies as well as the sea surface temperature anomalies also. And this feedback actually explains why we can expect a stronger active following a break, and that I will explain in the next slide. And what we can see here, similar Hofmuller diagram of net heat fluxes and latent heat fluxes in the contour as QNet as shading. What we can see by comparing this control and sensitivity run is the sensitivity run amplifies the flux feedback also, that is in terms of latent heat flux as well as the net surface heat flux also. And this also is reflected in terms of the diurnal warming or the diurnal range of SST, where we can see that the control run doesn't have that much of diurnal warming during the break phase and the following active phase. But here what we can see in the control sensitivity run, the diurnal warming during the break phase previous to the active phase is quite well represented. And similarly, the shallowing of mixed layered anomalies during the break phase of the monsoon is also quite stronger as compared to the control run. Similarly, during active phase, the mixed layer depth anomalies are deeper as compared to the control run. And this, because of this diurnal warming of the surface ocean, there is a lot of moisture and moistatic energy convergence that happens, which favors for a stronger active phase of monsoon. So this slide basically explains what is the impact of diurnal as well as the intraseasonal improvements. That is that it helps in improving the seasonal mean latent heat fluxes and rainfall anomalies. For example, in the control run, we have a lot of weight biases over the oceanic part, whereas over the land masses, tropical land masses, we have dry bias. But the dry bias over the landmass and the wet bias over the oceanic part is considerably reduced in the sensitivity run as compared to the control run. That is because of the enhancement in the diurnal amplitude as well as the intraseasonal amplitude of precipitation. So this is basically the summary of my slides. Basically explains the impact of resolving the diurnal cycle of surface ocean on different scales of prediction, and it also helps in improving the prediction skill of various climate monitoring indices such as ENSO, IOD, even the Indian summer monsoon rainfall index, and it also helps in improving the ENSO monsoon IOD monsoon relations. So this is an effective approach towards addressing multi-scale coupled model biases without modifying the convection schemes. So thank you. That's all from my side.
Thank you. Very interesting talk. We are a little behind because of the technical difficulties, so I'm going to skip questions. Maybe if you have a question, just try to contact Maheswar offline. Our next speaker is Kay McGonigal. Online as well. Okay, is Kay online? Yes, got a thumbs up.
Is my screen up?
We can see it in full screen mode. It looks good. Whenever you're ready, go ahead.
Great, thank you. Hi, everybody. Thanks for joining. Sorry I couldn't be there in Boulder. I'm Kay McMonagle. I'm an assistant professor at University of Alaska Fairbanks, and I'm going to talk about some work led by Sarah Larson when I was her postdoc at NC State University. And the topic is how ocean complexity shapes sea surface temperature variability in a CESM2 model hierarchy. And it's currently with minor revisions in Journal of Climate, so hopefully we'll be out soon. So our motivation is that identifying sources of climate variability is really a central question in our field with implications for predictability. So if we know where some sea surface temperature variability is coming from, maybe we can predict it. And in general, we'd expect ocean processes to enhance SST persistence due to a number of different reasons. So for instance, the high heat capacity of the ocean suggests that it should elongate timescales. We might have reemergence of wintertime thermal anomalies, and then we have the slow ocean dynamical response to processes such as Rossby waves. We also know the atmosphere can enhance persistence through things like the Bjerknes feedback and cloud SST feedbacks. And again, this is really a central question that many people have looked at over the past several decades, the reason being that it's complicated. So this is just a schematic. It's a really nice illustration of all the different ways that the atmosphere and the surface and ocean can interact. So we have surface wind stress, we have surface heat fluxes, our mixed layer depth is going to come involved here. And so it's a complicated question. So what we did is we broke this down by considering ocean dynamics in 3 different categories. So the first one I'm going to call local ocean processes. And if you're thinking of a model, this would just be anything that's happening in a single grid cell. It doesn't rely on communication with the grid cells next to it. So mixing, entrainment, and time varying mixed layer depth, essentially vertical processes happening in one grid cell. Then we have ocean dynamical processes. So these would be due to anomalous heat convergence due to any number of ocean dynamics, but things like the gyre circulations, overturning circulations, Ekman transports, and waves. And then thermodynamically coupled air-sea processes. So here we're thinking things like the Bjerknes feedback and the wind evaporation SST feedback. And one tool that has been used pretty frequently to look at the role of the ocean in different processes is a comparison of a slab ocean model and a fully coupled model. So a fully coupled model is kind of our typical model setup where we have an ocean and an atmosphere that are exchanging buoyancy fluxes, and the fully coupled model is also passing time varying wind stress to the ocean. In the slab model, the ocean model is swapped out with just a mixed layer thermodynamic, or a mixed layer model. And so generally speaking, the mixed layer depth doesn't vary in time. And then there is no momentum forcing on the ocean. To make the mean state of the slab similar to the fully coupled, usually a time invariant Q flux term is added. So this is kind of representing the time mean heat transport of the ocean. The problem with this is really the slab omits all of the ocean processes. So we don't have any of our local ocean processes. We also don't have any of the ocean dynamical processes. So if you're trying to explain why the slab model and the fully coupled model are different, you can't really pin it to a single dynamical process. And so what we did is we added in an in-between model hierarchy that we call the mechanically decoupled model. So that's the one in the middle here. And the mechanically decoupled model is just like the fully coupled model in terms of exchanging time-varying buoyancy fluxes between the ocean and the atmosphere, but we alter the momentum flux. So what happens is in the atmosphere will simulate some wind speed that's passed to the coupler. And then within the coupler, we overwrite just the wind stress forcing with a climatology. And so the mechanically decoupled model ocean is forced by a climatology wind stress and fully time varying buoyancy fluxes. This includes fully time varying wind speed here in these buoyancy fluxes. And so you can think of it as being kind of less realistic and less complex than the fully coupled model, but it does have local ocean processes and some ocean dynamics, unlike the slab. So it's really between the two. A few more specifics. We conducted this within CESM2, the 1 degree resolution version of CESM2, using pre-industrial forcing. And we constructed the mechanically decoupled model using a 50-year climatology of 6-hourly wind stress forcing. We actually took this directly from the seam coupler. So we reran 50 years of the fully coupled model to get that coupler output. And the reason for that is then we eliminate any potential issues due to remapping. And I'm going to show results from 600 years of analyses following a 50-year spin-up. Then the slab ocean model is constructed using 50 years of the fully coupled model to estimate the mean mixed layer depth and Q flux terms. And this was run by Dave Bailey at NCAR. Thanks, Dave, if you're in the room. And for this, I'm going to show 350 years of analysis after a 10-year spin-up. So when we're looking at comparing the mechanically decoupled model to the fully coupled, we're isolating the role of wind stress-driven ocean dynamics. And when we're comparing the slab ocean model to the mechanically decoupled, we're isolating the role of local ocean processes. Okay, so first thing I'm going to show is the mixed layer depth. So this is the mixed layer depth in different seasons in the fully coupled model. And you can see that the mixed layer depth is deepest in the winter hemisphere, as we would expect. This is the difference between the fully coupled and mechanically decoupled mixed layer depth in each season. So you can see this difference doesn't vary that much across the seasons. So in other words, we do have a reasonable seasonal cycle of mixed layer depth in the mechanically decoupled model. But you'll also notice that this is kind of blue in most places. So in general, the mechanically decoupled model mixed layer depth is slightly shallower than the fully coupled model because we have less wind-driven mixing when we get rid of those anomalous momentum fluxes. And this does make a difference in some regions. So for instance, in the Southern Ocean, short-term variability in wind stress is important to the mean state mixed layer depth. It isn't as important everywhere, but definitely in the high latitudes, it's an important term. Then we can look at the difference between the fully coupled and the slab ocean mixed layer depth. And again, the slab doesn't have a seasonal cycle in mixed layer depth. It's time invariant. And so you can see that these differences are extremely large seasonally. So if you averaged across this and looked at annual means, you would recover the same fully coupled mixed layer depth. But the differences are as large as 300% in some seasons. Next, we can look at the annual mean SSTs in each model. So on the left is ERSST, our estimate for observations, and then across the top are each of our model experiments. If we look at the differences then on the bottom row, fully coupled minus mechanically decoupled, this is mostly blue. So in other words, the mechanically decoupled model is slightly warmer, and we think that's because the mixed layer depth is a little bit shallower. If we skip over to the fully coupled model minus the slab ocean model. In general, the slab ocean model is a little bit warmer than the fully coupled, and we think this is due to the slab experimental design. So the way that that Q flux term is brought in, there can be sources and sinks of energy in the slab, and there could also be rectification of the seasonal cycle of mixed layer depth onto the mean. Next, we can look at SST variance. Again, observations to the left, and then each of our 3 model experiments. First thing we can notice is that there's very large differences between the fully coupled model and mechanically decoupled model in the tropics, and that's because the mechanically decoupled model doesn't have ENSO. So when we decouple mechanically decouple the atmosphere and the ocean, we shut down the Bjerknes feedback, and there is no ENSO present in that model. Looking at the slab, we see these bullseyes of really large SST persistence, and those correspond to the same areas where there's strong low cloud SST feedback. And so this is something that we have a NOAA grant recommended for funding to dig into deeper. Now, if we look at the ratio of fully coupled to mechanically decoupled SST persistence, we can get this picture. So it's mostly red. In other words, ocean dynamical processes due to anomalous wind stress are enhancing SST variance mostly everywhere. If we compare the mechanically decoupled model to the slab, this one is mostly blue. So in other words, local ocean processes are damping variance everywhere. And then on the lower right now is the fully coupled model over slab variance ratio. And you can see this is above 0 in some places and below 0 in others. So in other words, when we're looking at the total role of the ocean, it's really a tug of war between the damping by local ocean processes and then the enhancement of variability by ocean dynamical processes. And in different regions, different terms win out. We can then look at SST persistence. It's mostly the same story as the SST variance, just a little bit noisier. So in general, SST persistence is enhanced by ocean dynamical processes. It's reduced by the local ocean processes. And then again, in any particular region, either the ocean dynamical processes or the local ocean processes might win out when we compare the fully coupled model to the slab. And then lastly, we can ask what is causing the differences in SST variance. And so we decomposed the SST variance into 3 different terms. I'm going to call this first term on the right-hand side of the bottom equation the Q prime term. So this is due to anomalies in the net surface heat flux. The second term I'll call the H prime term. So this is due to anomalies in the mixed layer depth. And then the third term is our Q prime H prime term. So we can look at each of those terms in each of the models. So the top row here is the fully coupled model, and below it is the mechanically decoupled. And what I want to highlight here is that there is larger variance in the Q prime term in the mechanically decoupled model than the fully coupled model. And that's because the mixed layer depth is shallower and we're dividing by H in that Q prime term. We can put up the same decomposition for the slab, but because the mixed layer depth is time invariant in the slab, we only have that Q prime term, and it's much lower than in the fully coupled model. And the reason for this is because there's no seasonal variance in the mixed layer depth. So if you actually swap out this H prime with the fully coupled H prime that does, or sorry, H bar with this fully coupled H bar, which does vary seasonally, you recover something that looks a lot like the fully coupled Q prime term. But without that, we have lower surface heat flux driven SST variance in the slab due to that lack of seasonality in the mixed layer depth. So in conclusion, we find that the net role of the dynamic ocean is regionally dependent with competing effects from ocean dynamics and ocean damping. In general, wind stress driven ocean dynamics enhance SST variance and persistence, while ocean damping through local processes reduces SST variance and persistence. And it's worth keeping in mind that reducing your ocean complexity will change the magnitude of thermodynamic forcing of SST variability. All the mechanically decoupled model data is publicly available on Earth System Grid. And then I'm not going to go through all of this, but in the paper, we make some specific recommendations for things to keep in mind when you're comparing these models. And the most important part is that I think in both cases, you're actually underestimating the role of the process that you would think that you are isolating. Thank you.
Thank you, Kay. Do we have any questions in the room or online? Yes, one in the back. Justin, do you want to come up to the mic?
I just had a quick question. Towards the end, we were looking at what drove SST variability.
I can't hear you.
Oh, yeah. Thank you, Alyssa. Can you hear me now? Okay. The equation, but very nice talk, and the equation at the end did not have the Ekman heat transport part. Was there a reason for that?
Did not have the equation looking at the SST variance.
Yeah, I just wondered, you focused on the surface heat flux.
Yeah.
But there could also be an Ekman.
I don't have a great answer for that. I probably should have put up where the citation for where this came from. That would be a great thing to ask Sarah, though. I think we were mostly interested in if the net surface heat fluxes were different in the model, so kind of the role of those net surface heat fluxes, and less so on the Ekman component, but it would be interesting to look at the Ekman component as well.
Thank you. I'll look out for that paper.
All right, thanks, Kay. We're going to move on to our next speaker now. So, our next speaker is Shinru. Come on up. And in the back, if you guys want to push the slides.
It is the pointer?
Yes. So, the middle one goes forwards.
Okay.
That one goes backwards.
Okay.
And
Is it
then,
point the slides or
yeah, this
mouse?
is a pointer. Hold on. Yeah, you have to push and hold before
Push
it
and
comes
hold.
out.
Okay.
All
Thanks.
right, you ready?
Yes.
Go ahead.
Thanks. Hello, everyone. My name is Xinru Li. I'm postdoc at Princeton, working with John Cresting at GFDL and Gustavo here. Thank you for having me today to share my ongoing work on the extreme temperature events, marine heat waves in the global ocean of the upper 700 meter. So yeah, a little bit about why this is important or interesting. As many of you know, marine heat waves has caused increasingly significant ecological and socioeconomic impacts under continued climate change. Responding to the urgent need of the information on these devastating extreme events, there has been substantial efforts to understand marine heat wave, especially over the past decades. While marine heat wave at the sea surface is relatively well observed and digested, our understanding on the vertical structure of marine heat wave is limited. But heat stress at the subsurface can also have large ecological impacts and may also have larger influences on some biogeochemical properties, such as dissolved oxygen and pH, through affecting their solubility and transport. So they may also contribute to other ocean extremes. And so all this brought me to my research on better understanding the upper ocean marine heat waves. To do this, we use global daily ocean temperature outputs of the 100-year pre-industrial control simulations performed by the two fully coupled climate models, one developing version of CESM3 and GFDL CM4. So these 4D daily temperature data sets is huge. For each model is larger than 3 terabytes. They are unique, but also pose a big computational challenge. So we ended up with not using the existing marine heat wave detection package, but instead we compiled a more efficient version of Python codes for this work. And we also compared marine heat wave climatology represented by these two models and tried to understand the large differences. So while both models use model 6 as the ocean components, there are many differences in terms of the horizontal grades and vertical structures and etc. that may cause large differences in the simulated marine heat waves, such as this version of CESM3 includes the Z-star vertical coordinate and a nominal horizontal grade of 2/3 degree, while CM4 uses a hybrid vertical coordinate and a horizontal grade of 1/4 degree. For defining marine heat wave, we followed the Hobdays framework. As this diagram shows, when the temperature time series, as this red line shows, exceeding the dashed line, which is the 90th percentile thermal thresholds, at least over 5 days without any gaps longer than 2 days, that means a marine heat wave event occurs. And we also defined 5 metrics for describing the statistics of marine heat wave in each year, which includes the total number of marine heat wave events, that is the annual marine heat wave frequency. And for each day of the year, when temperature exceeds the threshold, there is a marine heat wave day. So we count the total marine heat wave day for each year as the annual total marine heat wave duration. And we also calculate the average of the daily temperature anomalies relative to this threshold as the annual mean marine heat wave intensity. And then we also identify the maximum of the daily temperature anomalies at the annual peak marine heat wave intensity. And lastly, we sum up all these daily temperature anomalies in each year as the annual cumulative sum of marine heat wave intensity. So the reason we chose these 5 metrics is because they imply different and critical ecological impacts, and also together they can describe the thermal structures of marine heat wave in each year. So in the next few slides, I will show you the results on the global patterns of pre-industrial marine heat wave characteristics in the upper 700 meters represented by the 2 models, and also talk about some large differences. Just to be clear, all the maps I'm going to show in this talk are the annual marine heat wave metric values of each year, averaged over the 100-year simulations. So it sort of represents a pre-industrial climatological state. And in interest of time, we choose to show the global patterns at the sea surface and the bottom of the euphotic zone, which is the 200 meter, and the bottom of the upper ocean 700 meters. So here for the frequency, both models simulate large values, more than the 3 events. in the tropics of the most 700-meter layers. And when comparing between the models, we see the CESM3 generally simulates less frequent events across most of the upper 700 meter, particularly at the sea surface. For the annual mean, for the duration, most of the upper 700 meters simulates the annual total marine heat wave duration over than a month. So any regions below, shorter than a month is indicated at the green regions. So we see a shorter duration at the deeper layer below the 400 meters, for example, at these 700 meter shows. Also together with the frequency, higher frequency we see in the tropics, it suggests the pre-industrial marine heat wave climatology in the tropics is more frequent but shorter. And here is another interesting feature is CESM3 generally simulates shorter duration compared to the CM4 by about 5 to 10 days, which may be partly related to the longer frontal lengths of MLE and the faster restratification timescales. For the annual mean intensities, both models simulate large values above the 1.5 degrees Celsius in the tropics and the northwestern Pacific and Atlantic in the upper 200 meters. Below the 400 meters, CESM3 starts to show small values, while CM4 still simulates large mean intensity greater than 1.5 degrees Celsius in the mid to high latitudes of the boundary regions. For example, here the CESM3 simulates a much smaller mean intensity than the CM4 over the Gulf Stream regions. Here at the depths of 700 meters. So this is a preliminary results. We have a hypothesis this might be related to its coarser horizontal resolution, as it commonly comes with the faster and stronger decay of the Gulf Stream with depths. In the second part, I'm going to focus on exploring the influence of model temperature drifts on the simulated marine heat wave climatology. Just to be clear, here the drift we meant the temperature anomaly relative to the first year of the pre-industrial control simulation, driven by the ocean circulation model formation, which is likely persistent and stable through the 20th and 21st century. So the temperature drift identified from the pre-industrial simulation is likely to continue affecting the temperatures and the marine heat wave simulations. And also considering the pre-industrial state usually often represent a fixed state as a baseline without the anthropogenic climate change impacts. So the trend in temperature kind of disrupt this representation. So the drifting in temperatures may be necessary. And so in this section, we calculated the linear trend in temperature in each grid cell, and we corrected the temperatures by removing the trend. And then we calculated the marine heat wave climatology based on the original and the drifted temperatures to evaluate the influence of the temperature drifts. So here I show 3 maps of the duration based on the original temperature minus the drifted temperatures. So it's still blue. Okay, so the negative values represents the, in the bluish, represents the drift-related underestimates, and the positive values in the reddish indicates the overestimates. And so for all the metrics, we examine the differences at each depth layer, but again, in interest of time, we still show 3 maps of the same depth layer, the surface 200 meter and 700 meters. And overall, we see non-negligible drift influences for all the metrics across the upper 700 meters. For the duration, so here you can see there are large underestimates in the mid to high latitudes of both hemispheres, and there are also large overestimates in the tropical regions below the 200 meters, particularly in the Atlantic. And again, as the global patterns, oh, sorry, I didn't show the global patterns of the annual mean, annual peak, and the cumulative sum heat stress intensity, because these three mean intensity metrics show the similar patterns. So again, here I show you the temperature drift influence for the mean intensity, which shows the large overestimates in the Labrador Sea and the Nordic Sea in the upper, in all the layer of the upper 75 meters. All right, in summary, here are three main take-home messages. First, we see more intense upper ocean marine heat wave characteristics largely appear in the tropics and the mid to high latitudes of the boundary regions. We also show many differences between the two models, which are likely related to the difference in the horizontal grid resolution and the associated ocean physics. And then we also, in general, say CESM3 simulates smaller marine heat wave characteristics across most of the upper 700-meter ocean at pre-industrial, except the annual mean, peak, and cumulative sum of marine heat wave intensity in the surface of the Northwestern Pacific and Atlantic. And lastly, given the prevalent large influence of temperature drifts on the simulated marine heat waves, the temperature dedrifting or a shifting thermal threshold should be carefully considered, especially when you're trying to detect a fixed pre-industrial marine heat wave state as a baseline. However, we also acknowledge there are caveats in our analysis. So first, we didn't remove ENSO signals from temperatures that many model uncertainty exist, which may dominate many differences in the marine heat wave climatology we see. And second, Hobday's 90th percentile thermal threshold is not perfect, so it can be problematic in some regions. For example, it may disrupt the statistics of marine heat wave in the polar regions when the sea ice develops or melts, because when the sea ice melts or develops, it can cause dramatic temperature shifts, which result in very distinct threshold levels, even with the smoothing. So what we see a lot of large signals in the polar regions may not be reasonable, so further analysis is required. And lastly, as I mentioned, this is ongoing work. We are also calculating the climatology of upper ocean marine heat wave characteristics over the more recent historical period, and for identifying any changes in marine heat wave climatology under the climate change. And we plan to run experiments to save heat budget diagnostics for identifying the predominant driving processes of the two periods, and may also identify any changes in the predominant drivers over time. And we also plan to compare the original and dedrifted model simulated marine heat wave against the observation for evaluating the impacts of temperature dedrifting on the precision of marine heat wave simulations. With that, I will stop here. Thank you for your attention. I'm happy to take any questions, comments, and suggestions. Thank you.
The next speaker come up while we're doing questions.
Oh, you mentioned the difference in the horizontal resolution, but do you think the different vertical coordinates could have an influence on this more variability in the GFDL model?
We expect different vertical structure can play a big role in the vertical structure of marine heat waves, but we just need to look more into what exactly that caused the differences. but that's on my to-do list. Thank you. If you have any suggestions to look, anything to look at, I'll appreciate it.
Thank you. All right, next speaker, and I see you have your laptop, but, okay. Good. So advance backwards, and then you have to hold this before it shows up. Shangling Ren from UC Riverside.
So, thanks for having me here. And I'm Shangling Ren, come from the UC Riverside, and I'm the fourth year PhD student. So today I'd like to talk about our recent result on the distinct anthropogenic greenhouse gas and aerosol-driven marine heat waves. And this work is working with my advisor, Wei Liu, he's here, and we collaborate with the Professor Robert Allen from UCR and the postdoc researcher Senyang Sang from the UCSB. Okay, yeah, so I think Xinyu has given a very specific definition for the marine heat waves. So here we will have a broad understanding of the marine heat wave. So marine heat waves are kind of the extreme warm water events. So we set up the 19th percentile of the sea surface, 19th percentile of the daily SST climatology as a threshold. And when the SST is higher than the threshold and persist for at least 5 days with no less than 3 days interval. So we say this is a marine heat wave event. And marine heat wave has a dramatic impact on the marine ecosystem, including the reduced biodiversity, altered the marine habitat, and also maybe a loss of the fisheries. And here, so in the left figure, so this left two figures shows a marine heat waves events occurred off the west coast of Australia in 2013. So comparing before and after the event occurred, so we can see that we can see the sharply decrease of the kelp population, and the ecosystem here has taken a huge hit, and it may need a very long time to recover. And as the global warming intensifies, so such events occurred widely across the world. So as shown in the right figure here, so we can see since the 1980 to the present, marine heat wave has shown a robust increase trend. I think, yeah, and this increased trend in the marine heat waves. This increase trend in the marine heat waves is temporarily consistent with the changes in the global mean surface temperature anomalies, like the figure A shows here. So this long-term warming trend observed over the past century, so it can be explained by the effect that human activities have had on our climate, like the greenhouse gas or aerosol emissions. So the CESM1 model shows that the greenhouse gas can trap more heat, causing the average global temperature to rise. And on the other hand, so aerosol may cool the Earth's surface by scattering and absorbing solar radiation, and also maybe affecting the clouds. So based on this, we speculate that the anthropogenic greenhouse gas and aerosol will influence the global marine heat waves. We want to explore how do the aerosol and the greenhouse gas affect the marine heat waves. Here, so we employ the probability density function to, which can help us to quantify and compare the changes in the marine heat wave under different conditions. In the figure, oh, I'm sorry. So it should be, yeah, in this figure, the light gray area so represents the likelihood of a marine heat wave events. And this area can be increased to the union of the dark gray and the light gray, the union of this area. So it can be increased with increase the probability likelihood of the marine heat waves by shift the PDF shape, the curve, or it can also by widening the PDF distribution. So and And we found that so anthropogenic greenhouse gas and aerosols can shift the mean state SST to modulate the Murray heat waves. Besides this mean state shift, so we want to explore can they alter the shape of the SST probability distribution to modulate the Murray heat waves. So we choose the OSST version 2.1 as our observations, and we also employed 10 semi-phase fully coupled climate models with all of their ensemble members, which have the daily SST output. And our time period we choose the last 4 decades from the 1982 to 2020. So in order to isolate the greenhouse gas and aerosol effect, so we choose 2 kinds of experiment. First one is a historical one and a single forcing one. So historical simulation is driven by the historical variation of all of the climate forcings, and the single forcing simulation is solely driven by the anthropogenic greenhouse gas or the aerosols. And here, so the daily SST climatology is distinct among all of these 3 groups of the simulations. And for each simulation, the daily SST climatology is calculated. So because of this, our methodology eliminates the effect of the mean state SST difference on the Murray heat waves. So we can see how the anthropogenic forcings can change the PDF shape to modulate the Murray heat waves. Here is our some result. So this figure on the right, sorry, the color. This on the right shows the performance of the Murray heat wave matrix in the OSST, the first column, and the semi-thick historical simulation, the second column. And the red column, so I just show the difference between the observation and the historical simulation. And we look at the 3 different metrics, duration, frequency, and intensity, to see the Murray heat wave performance. So it shows that the strongest and most persistent Murray heat wave event is always happened in the eastern tropical Pacific, and the short lifetime but very strong Murray heat wave events is always occurred near the Gulf Stream area and the crucial extensions. So if we compare the OSST version 2.5 and the historical one, so we can find this kind of distribution patterns of the observed Murray heat waves are well captured by our model, historical simulations. So so our next step is to explore how do the anthropogenic aerosol and greenhouse gas can affect the Murray heat waves. So here is our results show the global Murray heat wave driven by the greenhouse gas alone scenarios. So we compare the Murray heat wave in the greenhouse gas only experiment and with the historical simulations. So the the figure here, first column is the Murray heat wave performance in the greenhouse gas alone experiment, and the red column shows the difference between the historical alone and the between the greenhouse gas alone and the historical simulation. So from this result, if we only consider the effect of the anthropogenic greenhouse gas, more persistent and intense Murray heat waves are expected to occur more frequently over the global ocean. And so we did the similar analysis, but for the aerosol-only experiment. And so on the country with the greenhouse gas effect, so anthropogenic aerosol alone scenarios significantly weaken the Murray heat wave on a large scale, and also they suppressing their growth over the global ocean compared to the historical simulations. So we can see this opposite effect on the greenhouse gas and the aerosols. So to deeply investigate the impact of the anthropogenic forcing on Murray heat waves, we perform a probability density function analysis for the global mean sea surface temperature anomalies. And if you compare to the historical one, the green line in the middle, so the green line in the middle, the light green line. So the greenhouse gas alone shows smaller cortices, which implies that greenhouse gas alone fosters the occurrence of the of the climate extremes. But on the other hand, so instead, the aerosol alone suppress the occurrence of the climate extremes, as evidenced by the larger cortices. We can see the blue line here. if you compare the blue line with the middle gray line. And also the strong Curtis change not only affect the Morrow heat wave, and if we look at the tail on the, if you look at tail, oh, sorry. So if you look at the tail on the left hand, so you can see that the anthropogenic greenhouse gas alone will intense the cold climate extremes, but the aerosol alone will mitigate it. So, and also through the quantitative analysis, we found that based on the 99 percentile of the SST anomaly, so the Curtis difference in the greenhouse gas and aerosol alone experiment result in an increase about 0.25 degrees Celsius, but a decrease of the 1.35 degrees Celsius relative to the historical simulations. And if we compare the numbers with the mean state shift effect, so we can find that the effect of the Curtis on Morrow heat wave is comparable to that by mean state change. And here is our conclusion. So we compare the greenhouse gas alone and the aerosol alone experiment with the historical simulation. We find that the global Morrow heat wave show larger frequency, intensity, and duration under the anthropogenic greenhouse gas alone scenarios. But in the aerosol alone scenarios, it will show opposite phenomenon. And also we compared to the historical simulation, the global SST probability distribution, it has been expanded tails under the anthropogenic greenhouse gas alone scenarios, which indicating the promotion of the extreme climate phenomenon, like the heat waves, and maybe we will have the cold spells. And also here, so the aerosol only scenarios show the opposite result with the greenhouse gas alone. And we compare the effect of the Curtis and the mean state change, find that the effect of the Curtis on climate extreme is comparable in the magnitude to that of the mean state change. And so our results are published in this paper, and if you are interested, you can go through for more details. Thanks for your attention today.
Again, Gustavo's done the best. All right, so last talk of the session, Gustavo Marquez, and we're going to go in.
Good afternoon, everybody. I'm Gustavo Marquez. I'm going to give you an update on the status of MOM6 towards CSM3 in terms of what we're doing for the release, what we have done from after the winter working group meeting, and what we have like in the pipeline for the next few months, and then hopefully with enough time for discussions. So this work is an effort of a lot of people. I'm listing some of the people involved here, but there's many other ones, including in the other bays that are giving talks right now. In terms of our CSM workhorse configurations and choice of physics, you don't see the same as I do. Coding, apologies. What we have done in terms of being the out-of-the-box configuration since the winter working group meeting. So we've made the choice of using hybrid vertical coordinate going forward, and I will explain the reason in a few slides. We are still working on the wave processes and improving the vertical mixing configurations, and it's uncertain if that we'll be able to make that go through by the code freeze in a few months. We have made the vertical structure of ready a default, so ready and GM now are exactly the same in terms of the diffusivities. We are working on a backscatter scheme that Ian is leading, and it's very likely that will make it to the science freeze. We are exploring the length scale or prognostically length scale for the mixed layer eddies from Bonner et al., and I will show a few slides about that. So we're evaluating that, and that option will be available by the science freeze. We have implemented, and that was led by Frank Bryan, the Ullman scheme for the shortwave penetration that's just like in POP, and we're currently evaluating solutions with this option. We have implemented an option to do a kinetic energy conserving correction for the remapping of velocity. And then finally, we made a default, the subgrid scale equation of state corrections and geothermal heating. So that's out of the box, starting in CSM 2.3. What was the last version? I blanked out. 2.3 at beta 17, thank you. And then finally, the estuary box model will not be included in CSM3 because of the timeline. So as of the last time I presented, we had some trouble with the hybrid vertical coordinate. We were having loss of resolution near the surface. So there's a lot going on. This is an animation I'm about to show. So the colors show the layer thickness, and the light contours on the background are the layer interfaces. And then I'm overlapping on top of it the sigma 2, and I'm using the target densities from the HICOM vertical coordinate as the dashed lines. So when you see the dashed line parallel to the solid line, that means that the coordinate is isopycnal. And the red line on the top is the mixed layer depth. And I'm highlighting the 10 densest interfaces that we provide to the coordinate system with the dashed red lines. So this is to show where we're using the 10 target most dense 10 densest target interface that we provide to the coordinate. And you see it only happens in the Arctic and a little bit here in the ABW formation. So we see very thick layers within the mixed layer and the photic zone here in the Southern Ocean. And that was an issue that we identified the last round of simulations. So we were concerned about this. And the way we were able to fix it, it was by imposing a maximum layer thickness following this hyperbolic tangent shape. So we use the hyperbolic tangent function, but we do some manual edits near the surface. So this is just to assure that at every grid point, we have at least 4 vertical layers. So this is a 2.5 meter on the first 4 layers. And then we switch the hyperbolic function. The blue line is the maximum thickness that we used in the simulation that we just saw. So when now we switch with this new profile for the maximum layer thickness, now that same animation, we no longer see those yellow or very thick layers popping up here near the surface and within the surface mixed layer. So we are happy with this, and that's why was one of the reasons we decided to switch to a hybrid as our default. However, the current HICOM one, which is a type of hybrid coordinate, so that's the one we're going forward with, the current settings does not work with all climates. And this is a plot from Frank Bryan. So in blue, let's see if you can see blue. Yes, you can see blue, is the pre-industrial control simulation, and the solid line is the median, and the shading is the 5 and 95th percent quantile. And the dashed or the dot, the lines at the top and bottom, those are the target density interfaces that we have in the coordinate. So you can see that like as we go towards the bottom of the ocean, we have high resolution in the interfaces, so we're capturing well most of the ocean interior. That's where we want to be isopycnal. Now, if you do the same analysis, so this is doing every vertical level of the model, you compute the mean, and then the 5th and the 95th quintile. So now it's for the LGM, the last glacial maximum. So you're using CSM2 LGM data to make this plot. Now we're outside of that range of densities. So if you use exactly the same configuration, it will not work for this LGM configuration. So that is a problem. So we cannot represent the LGM with the current targets. However, it's possible to just shift these interfaces to make this high resolution shifted to the right, to densest interface. And we are working with Paleo working group to address this issue. So right now, that's supposed to be a red, is a no for last glacial maximum with the current settings. And this is the analysis for all the other climates that we have been working on. And again, thanks to Frank for checking these simulations. So for the Eocene is unsure if we'll be able to use the same coordinate. Sorry, for the Eocene is a no, but for the Pliocene is we are unsure. But for all the other ones, the same interfaces that we use for the PI control will work. So as I mentioned before, Ocean Model Working Group has decided to use hybrid vertical coordinate as in the default in CSM3, in particular the HICOM1 option. And the rationale for choosing the hybrid is it combines the best of all the worlds. So we have this, with a hybrid, you can use level coordinate near the surface, so have high vertical resolution in the surface boundary layer, and then switch to isopycnal in the interior, where mixing is mostly adiabatic. And then we have the option to do all the coordinates, for example, terrain falling near the bottom, which is not the case at the moment, but no, it opens up the possibility for improving the coordinate even further. And because we are isopycnal in the interior, there's less spurial mixing associated with mixing across isopycnals. So it mitigates this thermocline Warm bias. It also has a better representation of overflows. I will show a slide in a second demonstrating that. And also overall leads to a stronger AMOC than in the Z-star. The cons is there's the laws of upper ocean resolution, which we have addressed by providing this maximum thickness for the layers. Is less intuitive to configure. And we're still learning how to adapt it to make it work for different climates. So we're still learning how to work with this coordinate. And we will address these concerns. So if you're worried about not being able to use your diagnostic tools to work with this different vertical coordinate, don't worry. We have the option to output the variables in a variety of vertical options, for example, in Z or level, sigma 0, sigma 2, the native, and many other ones. And recognize that this choice might pose a challenge for when modeling different climates, as I mentioned, the LGM, and the Ocean Model Working Group is working with the other working groups to find solutions. Now moving to some of the metrics. So these are all the runs I'm going to be showing today. We have been doing these runs over the last few weeks. So this is all really new stuff. And the first, I'm going to show this global mean temperature in both forced and in coupled simulations. So in this time series, the long runs are the fully coupled. The one on the top is with Z-star, and the one at the bottom is with HICOM1. And we can see right away, HICOM1 cools relative to Z-star. That's not new. We tend to always find this, and others have found the same result. And then I have many forced simulation here. Those are the shorter runs. And I will just highlight again, we see HICOM1 being cooling relative to Z-star, and there's also this run with the Bodner length scale for the mixed layer eddies, which cools even further compared to our control hybrid. In terms of global drift of temperature, the top plot shows the Z-star simulation. This is coupled, and then the bottom shows the HICOM1. Again, we've run these two cases for 100 years, and it's clear that near the surface, we get a cooling for both of them, but as you look at below 200 meters or so, the Z star is significantly warmer. We're looking at here the mean, so there might be compensating effects, and we're looking into that. So we're understanding we also should be looking at the RMSE to evaluate if there is no compensating positive and negative effects that are canceling out in the HICOM one. Now, the same thing for the forced, and again, we tend to get a stronger warming in the Z star compared to the HICOM one. Interestingly, with the HICOM one forced, we get a cooling at depth. We don't know at the moment where this is coming from. Similar for salinity, so now global salinity drift, again, starting with the coupled, there is a fresh bias in both Z star and HICOM 1 near the surface, but that signal is stronger in Z star, and there is a salty bias at depth that's also stronger in the Z star. And this is similar for forced. So here, Z star is fresher near the surface for both coupled and forced, and also saltier at depth. Now switching to the Pacific equatorial undercurrent, the top left is the climatology based on the AGCP data, and this is at 140 west, and then the panel on the right, this is a simulation done with POP. So POP did a pretty good job in representing the equatorial undercurrent. And then on the previous simulations that we've been doing, we were underestimating the magnitude of the undercurrent. So these two simulations on the middle, so the one on the left, we're using the vertical coordinate just like in OM4, GFGL OM4 configuration, and we see a pretty weak undercurrent. So we are getting really thick layers in this region, and we think that's why we see a weak undercurrent. The one on the right, we were using the coordinate that I showed, the first animation that I showed, is slightly better than with the OM4, but no, it's still not as strong as in the OBS or with POP. And the reason that it was not that strong is because we were double counting on the background. We were prescribing the background diffusivity and viscosity twice, and we were overriding what we intended. So we want the Prandtl number to be between 1 and 5, but we were prescribing an additional background diffusivity and viscosity that was leading to a much larger Prandtl number below 200 meters in this region. So that's why we were killing the undercurrent and having not being as strong as in the OBS or in POP. So when we set then this background to 0, those are the two runs on the bottom, which are now, the one on the left is the HICOM one, and the one on the right is the Z star. We were able to get a much stronger undercurrent. And still, there is there's very little difference between HICOM 1 and Z star, but overall, with MOM6, we tend to get a slightly deeper undercurrent than in the OBS. So here is just deeper than 100 meters, while in the OBS is slightly shallower. And I want to thank Deepak Cherian for discovering this issue with double counting the background diffusivities and viscosities, and also for proposing a solution. So thanks, Deepak. Now switching to mixed layer depths. So this is winter mean mixed layer depths, starting with a couple cases. So the plot on the top right is the climatology based on the observations. On the top left is the Z star case, fully coupled. We're averaging between the last 30 years of the simulations from year 70 to year 100. And then on the bottom is the HICOM 1 simulation. Compared to the OBS, we are overestimating the mixed layer depths in the Northern Hemisphere for both Z star and HICOM. In the Southern Ocean, we tend to have too deep of a mixed layer depth in the HICOM 1 simulation. So now I'm showing the Z star minus the HICOM 1 here on the bottom right. And again, with the HICOM 1, we have too deep mixed layer depths in the Southern Ocean. And then the Z star is actually doing worse in the North Atlantic. That is, they're both too deep to begin with, but Z star is even deeper than HICOM 1. As I mentioned before, we've been evaluating the mixed layer eddy length scale scheme from Bodner et al. That was, the paper came last year, and it has been implemented in MOM6, mainly done by Abigail, which is the lead author of the scheme, and also folks from GFGL. So the GCMs use the string function to compute the mixed layer eddy effect, and there is this length scale in the denominator L sub f. And so far, we've been using a constant value of 1 kilometer. And with the new scheme, that becomes a function of the ocean state. So now, in forced cases, when we switched the Bodner et al., so again, top left is star, bottom left is HICOM1. Now, bottom right is HICOM1 plus this new parameterization. And right away, you can see that we shift the location of where the convection happens in the Labrador Sea, and is also slightly weaker. But above all, like, we are reducing the mixed layer depth in the Southern Ocean, which is where the HICOM1 was overdoing. So this panel is showing the difference between HICOM1 plus Bodner minus the default HICOM1. So shifted convection in the Labrador Sea, but overall reducing the depth of the mixed layer, which is a good thing. The shifting, I'm not sure. We're still trying to understand why it's doing that. And some people say it might happen, like it happens in OBS, but I don't have a good answer why is it shifting to the tip of Greenland. Now, this is a plot from Justin Small, again, looking at the winter mixed layer depth, but now focusing on the subantarctic region. On the left, we have the couple simulations, and the bottom left is the Argo climatology. And then on the right are the force simulations. And again, we can see, focusing on the force, that when we use the hybrid with the Bodner scheme, we are reducing the biases, which is a good thing. And in between the fully coupled is not as bad as in the forced, the biases. So we expect that as we turn on Bodner with this CSM3 hybrid fully coupled, it will be decreasing these biases that we are seeing here. Another plot from Justin Small, now looking at the eastern boundary upwelling system, in particular the Benguela region, so looking at SST biases. The top left is the POP low resolution. The top middle is the MOM6Z star, and top right is the MOM6 HICOM. So all the ones on the top are forced, and comparing the three of them, we can see that with MOM, we are reducing the SST bias in this region, and this is expected because, the hypothesis is because MOM has a high resolution grid that's closer to the GRA grid of half a degree, while POP is a nominal 1.1 degree. So that's why Justin suspects that that's the reason why we're improving the bias in this upwelling region. And then the bottom panels show the same analysis for the couple runs, and we don't see, there's a slightly improvement in the hybrid cases. In particular, if you look at the forced case, it's slightly better than the Z-star. To my eye here, the screen, the HICOM1 fully coupled is also slightly better than the Z-star, but they're similar and typical of the low resolution of couple models coupled to a low resolution atmospheric model. Now moving to the Nordics overflows, so starting with Z-star, we are looking at the mean density within 20 meters from the bottom, so this is sigma 2. And again, that's a Z-star case, so we're about to see an animation. I want you to pay attention, so the solid line shows the 1,000-meter isobath, and please pay attention to the overflows coming from this region, as well as on this region right here. So just to see how much of the dense water from on the shelf is being transported offshore. So this is with Z-star. So we see these pulses on the continental shelf, but not much of that dense water makes to the bottom of the ocean, in particular to the Imringer Basin here. So I'm going to skip for the sake of time. So now is this little, as I mentioned, little indication of dense water export through the major straits and troughs with Z-star. Now, if you look at the same animation with HICOM1, again, fully coupled, you see these blobs of dense water that periodically make to the Erminger Basin as well as here in this other basin. There's still a lot of room for improvement. We don't see much overflow coming through this little strait here, so we can probably do some topographic changes to make that happen. But no, I found this a very positive thing of the hybrid HICOM-1 option, that we can see overflows happening while we don't see the same with Z-star. Moving to the global meridional overturning circulation, so starting with couple, so these are averages over the last 30 years of these 100-year simulations. Top is Z-star, bottom is HICOM-1. They're both very similar, very little difference between them. Same is true with forced. The overturning is very similar in both cases. So there's not much to say here. Now, if we focus on the Atlantic meridional overturning circulation, again, starting with couple, with Z-star, we have these bull's eyes here, so this closed circulation, which indicates that there's got to be some upwelling happening here. It's pretty strong circulation. I'll show the time series in a second. Now, the bottom is the HICOM-1. It is not as strong as high latitudes, but overall, it is stronger at lower latitudes. So that closed cell is kind of spread over a wider range of latitudes. Now with forced is not as strong as with couple. And again, we see that the HICOM-1, which is the one on the bottom, is slightly stronger than the forced. So stronger AMOC in couple case compared to forced cases, and overall stronger AMOC with HICOM compared to Z-star. Focusing on the time series, so these are, the top is at 45 north. The top plot is for the Z-star control, so we saw that there was that blob of strong circulation, was a closed circulation in the Z-star, so that's the maximum within the region. With HICOM-1 is slightly weaker, but it's still pretty good. Now the bottom panel shows the profile at 26 north, and the maximum is stronger in the HICOM-1. Both HICOM-1 and Z-star are stronger than the OBS, and they both reverse direction about at the same depth, around 3,500 meters. If you do the same analysis on the on the force rather, the two cases are on top of each other at 45 north. And then the profile, so both cases are underestimating the magnitude compared to the OBS, with HICOM-1 stronger than Z-star. But interestingly, the depth of reversal, it is different between the two, with HICOM-1 being deeper than Z-star. We don't fully know yet why. One hypothesis is because in the fully coupled, there's other processes controlling the properties of the water, so it might be that things are not being formed well to begin with in both cases, while in the forced, like because it's a data atmosphere, so we're getting better characteristics of the water, the overflows, and that is being reflected in the HICOM-1, but not in the Z-star. Okay, so now I'm about to wrap up. 3 minutes, 1 minute past. So now going towards CSM3 code base, I've shown a similar slide a few months ago, and I'm adding some updates here. So we are here, the summer meeting, and things that we have accomplished. So Alper implemented the lane block elimination in CSM MOM6, and we have a gain of about 25% in cost by using this feature. Alper is working on the parallel I/O, and he will make this an option, or he will implement this and put it in the main branch between between the science freeze, which is in a month or so, and the release, so in the next few months. Bill Large has been working on is revisiting the vertical mixing option within KPP, including coupling with waves. And because that is done on a voluntary basis, it's unsure if we'll be able to make that go through before the science release. So there's a question mark on that option. The stochastic GME option that Ian Gruns is working on that will make the science freeze. We've been evaluating the Bodmer-Errol scheme, and we also are working on the enthalpy fluxes, revisiting the enthalpy fluxes with AMWG. It is uncertain if the enthalpy part will make it through the science freeze. The Bodmer-Errol option will definitely make it. In terms of size, there's CGrid option, which I think is very unlikely that will make it through, but also size is being evaluating, the size group is being evaluating the use of waves for the flow size distribution, and there's some uncertainty here too if they will be able to make that go through the science freeze. And then finally, the PGC Marble implementation is well on the way. We've been doing many force cases with Marble, and soon we will start doing fully coupled, so that will definitely make it by the science freeze. And as I mentioned before, the estuary box model option will not be an option for CSM3. Then in terms of tuning and model features, I just want to mention that first we've been pushing the eddy resolving quarter degree all in forced mode, and that's a work that's being led by Hussan, a postdoc with Ian, that's working on the CPT and eddy energy and transport with us. We are pushing the diagnostic package, and we work as much as we can by the release on it, and that will be part of Cupid, the effort that Dave Lawrence mentioned in the morning. We are continuing to do topography and channel changes. As I mentioned before, like there is that overflow that we can probably carve some of the topography to make it go through that basin I was showing in the animation. We have done a few since the beginning of the year that helped improve biases that we identified. We made the geothermal and stochastic density already an option, and that's out of the box. We made a decision to go forward with a hybrid vertical coordinate. We are continuing to assess bias with other working groups and try to mitigate them via tuning, and we'll be doing that until the very end of the release. In terms of ongoing development, there's a lot of the MOM6 is an open development model. There's contributions coming from many other institutions, and we are always taking advantage of those. So there might be new physics that come from outside of NCAR that if we find it suitable, we'll take advantage of them. We are working on a manuscript that will describe the workhorse configuration following an OMIP protocol, and we also develop a user guide for the CSM MOM6. We came up with this OMWG Dev repository that has a discussion page, and we are keeping all the discussion associated with tuning and model features on that location. And that's all I have. Thank you so much. I'm happy to take any questions. Picture?
Are they doing the picture already? Yeah. Let's do it. Right at 3? Well, too late. Did we miss it already? Go ahead.
Thanks to everyone for all the work comparing the two. Thank you.
You're welcome.
Anyone who wants to come back after the picture is welcome to come back and participate in the discussion. So I guess we'll go out now.
Yeah.
Every year you do these things, yeah. of talks, and then we had that filled. What we've decided is that the person who, Frank Bryan, who was going to fill in, has graciously offered to just let us have the discussion then, which I think works better. I'm sure there's people out who, even in here, who would rather be out there now. So no discussion during the break here. We'll do the discussion in the midst of the talks in the next section. Yeah, so we've got time. Come back at half hour.
Hey, Paul, are you online?
Yeah, I'm here.
Can you please get ready to share your screen?
Yeah, sure. Whenever you're ready.
Okay, I'll let you know in a bit. Thank you.
Sure.
Okay, let's get started. Welcome to the second part of the Ocean Talks. Before I pass it to Paul, I just want to say one more time, we missed the discussion on the CSM3 development on the ocean component, and I apologize for that, but luckily we have someone that dropped. So Rami Pages is not presenting, so that's at 4:15 p.m. So we will do a discussion at that time. We have 15 minutes to do the discussion. So now I'll pass to Paul Hall. Paul, please share your screen and go ahead to get started.
All right. Does that show up for everyone? Can you see the screen? Okay, great. Thank you for having me here today. I've got just a couple of slides. Hopefully we can get some discussion in here, because really what I'm looking for in giving this talk is some feedback from the working group and from the community about how to move forward with creating a theory waves component for CESM. I talked about this a little bit at the winter group meeting, but that was focused more on the longer term goals of what a component like this would be. And right here, I'm looking at more of a short-term focus on, how do we actually get this into CESM before we worry about rationalizing it with the other wave models that are out there. So for those of you who don't know me, I'm a software engineer at Brown University, where I'm working with Baylor Fox Kemper. I've been working with him on theory waves the last year or two, maybe a little bit longer at this point. I lose track. And some background on theory waves itself. The idea of theory behind theory waves, and this was developed by Ching Li and Baylor in Ching's papers from 2016 and 2017, is that we want to be able to look at the effects or incorporate the effects of enhanced vertical mixing due to Langmuir turbulence into global climate models like CESM. That can be done in a direct way using prognostic wave models like WaveWatch 3, but that's computationally expensive, prohibitively expensive. So theory waves, the model that Ching developed, is a simplified model based on empirical wave spectra that is, trivial to compute. They're trivial to compute. The computation time involved is very low, and but reproduces much of the effect that you see, in particular from calculating a Langmuir turbulence enhancement factor based on Stokes drift profiles from these empirical wave spectra. And over here on the right, you'll see this is a snapshot from Ching's 2017 paper showing, the observed summer mean mixed layer depth observations. Here's a control run with no waves in panel B, WaveWatch 3 in panel C, and then with theory waves in WaveWatch in panel E. And this was calculated. The theory waves component was calculated offline in this case. And you can see that in this theory waves, this simple analytical approach or empirical approach does a pretty good job and compares well with WaveWatch 3 at a fraction of the cost to actually implement it. Okay. This empirical approach is based on WinC only. There's no swell. It's based on Phillips spectrum wave approach, and also some along the way we use Pearson-Moskowitz too. But the model itself for input only requires three parameters. You feed in velocity, wind velocity at 10 meters, wind stress, and the boundary layer depth, and you can get out a whole suite of parameters that are useful. So the Langmuir enhancement factor, there's a surface layer average Stokes drift, you get out the surface layer average Langmuir number, Stokes transport, peak wave number from the Phillips spectrum, you get a significant wave height, peak frequency, and mean frequency from the Pearson-Moskowitz. All of this is available to us then as outputs from a wave model in a coupled system relatively inexpensively. Okay. This is just the set of equations that constitutes the actual model behind theory waves. And this is what we actually implement. And our idea here is that we wanted to develop this as a standalone replacement for WaveWatch 3 within CESM. So you could drop it in as a replacement component. So if people wanted to run a global model and you have to make the decision, do I run it with waves to get the enhanced Langmuir turbulence, or the enhanced mixing due to the Langmuir turbulence, or do at the cost of the computational complexity, computational cost overall, this provides a cheap alternative. Okay. So where are we currently? And since the winter meeting, I've updated our version of theory waves. I've implemented it now as a drop-in replacement for WaveWatch 3 locally, based on and it works with the CESM 23 Alpha 17A tag, which was the most recent tag available, I believe, at the winter meeting. So after the winter meeting, I updated it so it now works with that version. And I based it on to create these this component. What I've done is I've taken the WaveWatch 3, in this case the Dev Unified 0010 tag of WaveWatch 3, which again was the most the one that was currently working with Alpha 17A of CESM 23. Hollowed out the guts and replaced it with the theory waves model. This has the advantage of we're actually making use of reusing all of the Nuopsy cap, for instance, for WaveWatch 3. We didn't have to write it ourselves. We just sort of stole it from the WaveWatch 3 component, and all of the output routines are the same. All we've done is we've short-circuited any WaveWatch 3 calculations. We're using the input and output from the existing modules. This version works with the wave development comp sets, so GMOM, JRA, WD, and it works on the TL319, TO61, WTO61 grid right now. Okay, so that's where we are. Long-term goals, I talked about this at the winter meeting. The long-term goal is to have a fully interchangeable wave model components between theory waves, WaveWatch 3, and Pickles, MoMA Hell's model that's in development. And to do that, we need to standardize output from wave models, what's going into and through the mediator there. The short-term goal, however, and this is what was initially driving theory waves, is that we want theory waves to be available for people to use with CMIP7. And so this is where I've come to you, or I'm coming to you to ask for some guidance on this. CMIP7 is what's the appropriate CESM target for us for CMIP7, for use with CMIP7? Is it CESM 3.0? Is it CESM 3.1? How do we get this component that we've developed in as an option for CESM going forward? So again, what I'd like input on from you guys, and we can start some discussion. So which CESM release should we target for theory waves? What release tags should we be using to ensure the compatibility with the CESM 3 or 3.1? going forward? What are the requirements for getting this? I mean, we have an operational version of theory waves that's in, like I said, Alpha 17A. What are the requirements to actually get that incorporated into CESM as an option for use in whichever the 3.0 release or the 3.1 release, whichever one's appropriate for, CMIP 7? Do we need to provide separate comp sets, separate grids? Right now, we're working off of, since we're just copying the IO and, the IO from WaveWatch 3. In theory, any WaveWatch 3 grid that exists, we can just use. So that should be straightforward. And then another question is, what testing? Is there testing that's required to actually incorporate this component into CESM or not? And an important caveat here is that in terms of scientific testing, all of the actual theory wave models actually already exists within CESM2 in MOM6 because it's part of CV Mix. It's an option within CV Mix. It's just that as it sits within CV Mix, it's very hard to actually choose to include in a run. It's not easy to configure as a user. So part of this idea of splitting out the module, splitting it out as its own modules to make it a very simple configuration and option for users to use. But the underlying equations are already in the model. So that in some ways, this is more of a refactor than new science going into the system. But if it's new science, if you decide it's new science and we need to do some testing for validation, what test scenarios do we need to run? And what parameters should we be using to actually evaluate whether or not the theory waves module is up to snuff for this? And then finally, can we establish a timeline and a series of steps that we need to take in order for us to move from us having theory waves on our machine locally to, getting it into CESM and generally available to the public? And anyway, on that, those are my questions, and I'd be very happy to hear some discussion of this. Thank you.
Thank you, Paul. We have time for a few questions. Gökhan, go ahead.
Clarify why the theory wave is in CV Mix?
So the Langmuir enhancement factor operates on the turbulent velocity scale that's calculated in CV Mix. And so Qing incorporated the code into CV Mix, 5 years ago, 6 years ago.
I have one question. So going to what parameters should be, not parameters, but what the development that is being done right now that use waves relies on the Stokes velocity, both in the ocean and sea ice. And that's not a variable that you are currently providing, right, with the existing framework. So is it possible to get Stokes velocity with theory waves?
So we provide it. We get the surface layer average Stokes drift velocity. Is that I think, yeah, the surface layer average Stokes drift comes out of it. Is that what you're looking for? Just the Stokes drift velocity?
I think what we're looking for is the Stokes velocity at the surface, and then we just use the exponential functions to make
tail.
it.
Yeah. No. Yes, that can be provided.
Yeah, I think that is a must because the existing development in both ocean and sea ice rely on that. And if we suddenly add an option that does not provide those fields, it will be a showstopper for these developments.
Yeah, no, when we've had this discussion with Brandon Reichel, for instance, about trying to figure out how to provide output that would be consistent with his approach, which uses 5 different frequency bins and a tail, right, with an exponentially decaying tail on each. And I think the idea is that we could provide, because theory waves is just based upon the wind sea, that we would provide basically one frequency bin with the exponential decay associated with that, and the other bins we couldn't provide, but it would provide the high frequency component basically.
Yeah. Okay, thank you. Keith?
If this was included in CESM, who would be responsible for maintaining the code moving forward and documenting it and providing support? That's a very important part of CESM. It's not a drop the code in there and walk away. CESM is a community supported model, and we need to provide support to the community for everything that goes in there. Where would that support come from?
That's an excellent question, and I would defer to the group on this because, you know, how do we handle support for community developed components in general?
Justin?
Maybe a related question of interest is, it'd be good to get advice on when to use different options, like when is it good to use WaveWash 3, when is it good to use pickles, when is it good to use theory waves? And that, it might be good to think in the broader context of the wave modeling as a whole, this kind of question.
Yeah, I think that's a wonderful question. But right now, the choice that we have is WaveWatch or nothing, and this is sort of, you know, if it's the difference between that, you know, having everything and having nothing, this is an intermediate case where you can have waves at a low expense, and then yeah, once Pickles is ready, we can start having those sorts of discussions about what are the optimal applications for each of these different models.
Okay, thank you very much, Paul. Let's move to the next speaker, which is Liz Maroon.
Forward in slides, I click this middle one again? Cool, okay. I feel like in the last 2 years I've gotten old and I can't figure out technology anymore. Okay, so thank you very much for the opportunity to speak. We're switching spatial scales here from waves to the Mid-Atlantic Ridge. This is some work that I've been working on a little bit on the side for the past year or two, and I want to thank Andrew Shao for being willing to help me with this, but any mistakes, wild exaggerations, or comments today are all my fault, not Andrew's. And again, thank you for some of the core hours to get this off the ground from the working group, as well as to Wisconsin for funding me to do it. So let's talk about the Mid-Atlantic Ridge. This is one of the examples of where teaching actually influences research. I teach a graduate level class on physical oceanography that's taken primarily by meteorologists. To get them excited, we usually read a few chapters about the discovery of the Mid-Atlantic Ridge and Marie Tharp, and this is the Heisen and Tharp map, the artist rendition. And so I've been staring at this once a year, every year, for the past few years, starting to wonder, you know, what does the Mid-Atlantic Ridge do to the ocean and then to climate? What happens if you were to take it out? And, you know, I have a passing familiarity with Steve Yeager's work on topographic coupling, and so I started diving into the literature to figure out, has anyone actually done this? Has anyone taken out the Mid-Atlantic Ridge in a climate model, or an ocean model for that matter? And I couldn't find the simulation. So I thought, wow, this is interesting, because this is kind of the stuff that atmospheric scientists did in the 80s and 90s. I'm thinking like Held and Kutzbach with the Rockies and the Himalaya. Like, wow, I found something that hasn't been done. This is neat. But just because a simulation hasn't been done doesn't mean that you should necessarily do it. And I think there's some, right, come on. I mean, this seems like, you know, far-fetched. Why should we take the Mid-Atlantic Ridge out? I think there's two really good reasons. The first is inspired by some of the work by Sarah Reagan's PhD that she just finished up at University of Washington. She has developed an idealized version of MOM6 or MOM5 coupled to AM2 with square basins, square continents, and as she changes the northern extent or the width of the basin, she's found some very unexpected results in the organization of thermohaline circulation. And if you can get very strange organizations counter what we see in theory with very simple model like this with flat bottoms, well, if you're not even counting in bathymetry in that, what does that actually do? What I'm starting to think is that the ocean may be way more sensitive to the particulars of the continental configuration and to bathymetry than we give it credit for. And second, Steve Yeager had a great paper in 2020 where he found that part of the predictability mechanism in the subpolar North Atlantic is happening over the mid-Atlantic ridge. So for me, removing the mid-Atlantic ridge, what we're going to do is an experimental confirmation or not, test that idea that it's really the bottom pressure torques over that area are really important in that mechanism or not. Today, however, I'm just going to be talking about the mean state and leave variability for another day. So let's first review some of the key pieces of what the mid-Atlantic ridge does in the ocean in observations. So first, it acts as a barrier to deep abyssal flow. So for example, if I can get this, there we go. So for example, the Mid-Atlantic Ridge in the South Atlantic, along with the Walvis Ridge, really blocks Antarctic bottom water from getting into the eastern South Atlantic. The only place it can happen is like at this fracture zone. So where it can't happen, we can't get that across, so you have the flow being directed by bathymetry. And similarly in the North Atlantic, the Charlie-Gibbs fracture zone really acts as a conduit from water from one side to the other. So Labrador seawater crosses sort of an intermediate and deep depths to the east, and then overflow waters from the other side cross below it the other way around. Where you can't cross, you will get flows along the flanks of the Atlantic Ridge. So for example, the Mid-Atlantic Ridge is an important conduit for some of the interior southward pathways of the AMOC. There's a nice paper by Jai et al. Roughly 2021 saying about 10% of the AMOC southward flow is along the Mid-Atlantic Ridge. In the upper ocean, you can see most of the impact of the Mid-Atlantic Ridge in the North Atlantic, not the South Atlantic. So for example, you've got this great deviation around the Reykjanes Ridge that comes from it having to meander south. And then over on the Azores, you also have a bit of a deviation. Some of the flow goes around that way. So it acts as a barrier to the deep water masses. It steers flow in the upper ocean. And then what I'm not going to touch on at all in this project is the effects of mixing. So when you have rough terrain, you can get extra mixing. So really, what I'm going to try to do in this talk is talk about what is the presence how does the presence of the North Atlantic part of the Mid-Atlantic Ridge affect the mean ocean state in the horizontal, in the vertical, and then near the surface, and then talk a little bit briefly about what its climate impact might be through its impact on the sea level pressure field. So how did I do this? This was fun. So I took the Mid-Atlantic Ridge and I removed it in CESM2 by going model Y by model Y and filtering out some of the lowest zonal wave numbers in the spatial space, so in KMT, from roughly 20 north to Iceland. So I started from the CESM2 pre-industrial bathymetry here, and then on the right I have the simulation we're calling Flat Atlantic, where you can see that we've lost the Mid-Atlantic Ridge through the filtering. You will notice also, however, that it's not exactly flat. We've been able to preserve the gradual southward dip towards the abyss from Iceland down to south. So it's not exactly flat, but sort of. I've branched this from the CSM2 pre-industrial control, ran it for 100 years, and then used the last 50 years for averaging. I brushed over a lot of the details on how I actually got this configuration to work. Thank you very much for the Paleoclimate Toolkit from Nan Rosenblum and Esther Brady and Betty Otto-Bliesner. That got me 95% of the way there. And then thank you also to help from Mike Levy and Keith Lindsay for the rest of the 5%. There were some weird marble errors in the first version of this, and then there was also some overflow stuff that I had to bypass. So let's first talk about what happens when you move the Mid-Atlantic Ridge to the gyres. On the right here, we have the pre-industrial control simulation. Shading is the change in barotropic stream function. Contours are bathymetry every 1,000 meters. I've highlighted 5,000 meters in black just for a little extra context. And on the right here, we have the same thing, but in the flat Atlantic simulation. What you can see is that the subtropical gyre is weaker, so those stream functions are more compressed towards the west, and you've lost maybe 10 to 12 sphere drips in that northern half. You'll notice you've also had an expansion a little bit of the subtropical gyre. It now reaches a little bit further north. You've lost most of the meanders over the Reykjanes Ridge as much as I was able to remove it, and the subpolar gyre has become slightly stronger. Here's a different view of that. So now I've got in shading, this is the difference in the barotropic stream function, and then the contours are the pre-industrial controls barotropic stream function for context. So you can see that the northern half of the subtropical gyre has strengthened. We've got this northward expansion, so this red area represents, if you were to imagine these black contours stretching up this way, you've kind of contracted a bit of the subpolar gyre as a result, and you've gotten the strengthening where you've removed those meanders over the Reykjanes ridge. Part of the idea is to go back and look at studies that have tried to diagnose the impact of bathymetry using, say, like a barotropic vorticity equation, and figuring out how much of the bottom pressure torque is contributing to these. So if you look at Steve Yeager's 2015 paper at the effect of bottom pressure torque, you probably could have, the patterns in this region are very similar. So this looks like very much like the diagnostic part of bottom pressure torque. However, what's going on up here between about 50 and 60 looks very different. I haven't exactly figured out what's going on there, but there's a different balance going on besides just what's going on between wind stress, bottom pressure torque, and the adjustment in the transport. Cheryl?
Can I ask a really dumb question?
Yeah.
Bottom pressure torque thing is like a vorticity parameter?
Yeah. So, you have flow that hits the mid-Atlantic ridge, or flow that hits the western boundary and effectively pushes on the Earth. So if the whole world is trying to, take away the momentum from the spinning Earth, some of it comes from the ocean pushing on it. And you can get a vorticity term for that. And because vorticity must be conserved, the ocean has to adjust the bottom pressure torques, the meridional transport, to balance out the wind stresses. And the other terms too, but those are the three big ones on a basin scale. Thanks. So here is the meridional, thank you very much for the segue to barotropic vorticity equation. This is beta V, the planetary vorticity advection. Just treat it like it's the depth integrated transport. And so on the left here, we've got pre-industrial control on top, flat Atlantic on the bottom, and then the difference in the transports, beta V. And then I've got arrows there to indicate changes that are southward, anomalously southward or northward. So let's start with what's going on in the subtropics. So here you can see we have an anomalous northward transport on the other side of the Azores. And that's coming from, you've removed the Azores so you don't have that balancing area anymore. And that happened pretty much instantaneously. You took out the Mid-Atlantic ridge, it adjusted within a month pretty much. But it took longer for things to adjust as the signals propagated westward. And so you also see that the Gulf Stream has weakened as a result of removing the Mid-Atlantic ridge, quite far away, in fact. You also see similar changes over here and around where the North Atlantic current originally was. So the North Atlantic current has weakened, and to compensate, you have stronger transport now right up against the Grand Banks. And then you can also see that these meanders, you no longer have a meander over the Reykjanes ridge. So I'm going to skip forward to what does this do to the surface fields, because that is pretty much a gyre story. So here, this is the change in sea surface temperature in flat Atlantic minus pre-industrial control, and then I've got the anomalous barotropic stream function and some arrows to help guide your looking. So basically what's going on is the gyres have changed and they're advecting the sea surface temperatures along with it. And this adjusts within 10 years. So for example, we have anomalous transport this way, and that's transporting relatively warm and salty eastern subtropical water towards the Labrador Sea where it's colder and fresh. And similarly, you're transporting relatively colder and fresher water towards the east. And then similarly, you're transporting on this side slightly warmer and saltier water northward and relatively colder and fresher water southward. And then down here, this is the perhaps the more intuitive way to explain it. That's just a weakening of the Gulf Stream. You're transporting less heat poleward. The order of anomalies is roughly 1.5 to 2 degrees Celsius. So not huge, but notable. Salinity follows the same kind of thing. You change the advection by the gyres, so you've changed the position of where the sea surface salinity isohalines are. This is probably what I'm going to call the climate impact. So this is the Icelandic low. I've got sea level pressure in the pre-industrial control in the black contours, and then the shading is the change. So we have about a 1-ish, a decrease in the low pressures just to the south of the Icelandic low center, and then an increase in sea level pressure by about 1.5. to its north. So this represents a very slight southward shift to the Icelandic low, so slightly a more NAO positive state. The NAO time series, however, doesn't really change. The statistics are the same. So really quickly, going to show the changes in the AMOC and CESM. So here in contours is the pre-industrial control AMOC, and shading is the change. At the surface, you'll see there's a couple of up to maybe 5 sphere-drop changes. Those are actually quite complicated three-dimensional shifts of currents, so it's not like you have in any one place a little overturning. It's a three-dimensional response. And down in the deep, you have a decrease in the southward flow. This comes from removing the Mid-Atlantic Ridge. You've gotten rid of that interior pathway. So I will note that this is a pretty modest change compared to the first simulation that Andrew Shao and I ran with MOM6, an ocean-only simulation where we failed to get an AMOC altogether in our simulation. So I think this might be a model-dependent result, and we're going to go back and figure out if that was a quirk in what we did, how we set up the simulation, or something more interesting. So stay tuned. So in summary, removing the Mid-Atlantic Ridge weakens but expands the northern part of the subtropical gyre. It strengthens the subpolar gyre by taking out that Reykjanes ridge. Gives you sea surface temperature anomalies of about 1.5 degrees Celsius, sea surface salinity anomalies about 0.3 PSU, shifts the Icelandic low slightly southward, and it weakens parts of the AMOC, including that deep interior pathway. So this is, the first in a part of a project I hope will go on for a few years. One last thing I would like to say is I submitted this as part of a proposal last year, and the reviews I got back from the panelists and the ad hoc reviewers were just really fantastic. And I know that it's a small community, so there's a good chance that somebody who reviewed it is listening or on here. And I want to thank you very much for the great critiques and the great ideas, and do know that I am incorporating them as I go forward. And with that, happy to take questions in the last minute we've got.
Thank you, Liz. We have time for one quick question.
So in paleoclimate, sometimes we don't know exactly where the ridges are. So I was wondering if you have a sense of if you were to shift the position of a ridge, would that change things dramatically the way you're seeing?
Yeah, I have thought about that. That's kind of one of the other motivations for this work. I think it probably depends on the depth of that ridge. So in the South Atlantic, the Mid-Atlantic Ridge isn't as close to the surface, so it doesn't have as much of an upper ocean impact. Whereas in the North Atlantic, it's closer to the surface. The Azores is not really part of the Mid-Atlantic Ridge, but it pokes out to the surface. So I think that is something you do need to consider with paleoclimate simulations, is how close to the surface are these ridges, and would they impact the simulation by a couple, maybe a degree or 2 Celsius, or change the gyre circulation pretty significantly. Yeah.
Thank you. Okay, James, please come here. Our next speaker is James Larson. Feel free to go ahead.
Okay. Hey everyone. We've probably reached that time of the day when most of you are thinking more about whether you're going to take beer or wine in the next hour than about the western boundary currents, so I'll try to keep this engaging. So I've been doing this work as part of my master's thesis at Colorado State University, advised by Jim Hurl and Dave Thompson. Thanks to those guys for their generous advising. So we're going to start with a little bit of literature review, talking about a paper that Minobe et al. Published in 2008, where they forced an atmospheric GCM. Oh wow, the colors are so different. They forced an atmospheric GCM with the climatological SST patterns, specifically how the SST gradients are very sharp in the Gulf Stream, among other western boundary currents. When that atmospheric GCM is forced with those sharp SST gradients, you get a precipitation response, which is very similar to what is seen in observations. However, when you smooth out those SST gradients, the spatial pattern of the precipitation is quite diminished, both in terms of intensity and in spatial extent. But this paper focused a lot on the time mean response. This analysis is based on a 4-year time mean. We, for this study, aim to continue the same line of thinking, but more focusing on the climate variability aspect. Another way to think of that is, are SST anomalies strong enough in magnitude to influence the overlying atmospheric circulation, specifically SST anomalies in the western boundary currents? I want to clarify. So for data methodology, we're going to start off looking at ERA 5 over the period 2007 to 22. If we have time, I'll discuss more about that later, why. And then we also are looking at the IHES experiments. You have a 1 degree low resolution and then a 10th of a degree resolution ocean and a 1/4 degree atmosphere for 250 years of no CO2 transient forcing. All results are based on monthly mean anomalies, and all results are for the extended winter time where you find the air-sea interaction signals to be strongest. So we can get into it. We're going to start off just by looking at the Gulf Stream. Here I'm showing a plot of the standard deviation of SST anomalies in the Gulf Stream. You see that really strong, prominent pattern where the ocean dynamics are strongest for the Gulf Stream, especially when you look relative to the internal ocean basin when there isn't as much variability happening. If we then regress atmospheric vertical motion at 850 hectopascals as a function of grid point onto these SST anomalies, we find that vertical motion is highly covariating with the underlying SST anomalies. And additionally, when you look at that internal ocean basin away from that western boundary current, we're seeing that there's much less air-sea covariability happening. And this is not only true with the vertical motion, but it's also true for the precipitation as well, that over this western boundary current, we're seeing a lot higher coupling of these air-sea interactions, particularly over where the ocean dynamics are the strongest. And I'm going to rearrange the slide so now you've got standard deviations on the left and the 2 regressions on the right. And we're finding that it's not just the Gulf Stream that we're finding the signal in. When you look at the 5 major western boundary currents across the globes, I've got, see if I can get this laser pointer to work. You've got the Kuroshio east of Japan, the Agulhas current on the southern tip of Africa, the Brazil-Malvinas east of South America, and the Eastern Australian current east of Australia. In all of these western boundary currents, where you have heightened SST variability, which we know to be mostly driven by ocean dynamics, you're seeing this heightened air-sea covariability. With the most pronounced regions really tightly following that underlying region of ocean dynamics. I'm not showing it today, but if you would like to see it later, I'd also like to point out that all of these main features are statistically significant. And if you then take a spatial mean, if you look at vertical motion beyond just 850 hectopascal, if you perform this grid point-wise regression onto the vertical levels above 850 hectopascals into 500, even 200, and then you take a spatial mean of the regression coefficients, we can find that this spatial pattern, which I was just showing you, is extending above 850 hectopascals, which normally we think of where the boundary layer may just lie. That this air-sea covariability above these western boundary currents is extending into at least the middle troposphere, as additionally indicated by the sort of percent confidence panel that we're showing on the right. We find this to be one of the more novel aspects of this study because it's above the boundary layer where these anomalies can start to interact with the overlying circulation, with teleconnections, and the storm tracks. And it's not just in the ERA 5 reanalysis that we're finding this result. When we look at the IHES resolution, IHES experiments, or what I'm finding to be now called CSM high resolution, here I'm showing this same grid point-wise regression of vertical motion onto SST anomalies. ERA 5 on the left, which is what you've now seen, now incorporating the high resolution, CSM high resolution in the middle, and then the low resolution. We see that you really need that high resolution atmosphere and ocean in order to reproduce the signal. And this holds true for nearly all of the boundary currents, with the only slight exception being the Kuroshio boundary current, where you do have a bit of a signal, but even still, the spatial extent of this air-sea covariability is not nearly as strong as what's seen in the ERA 5 reanalysis. And one other figure that I would like to point out is that it's not just the resolution in the CESM model that makes a difference. We're also finding that within the Era 5 reanalysis, the resolution of the underlying SST data set, which is forcing this atmospheric reanalysis, is also playing a difference. In 2007, ECMWF switched their underlying SST field from a 1 degree field to a higher resolution 1/20th degree SST field. And we're finding that at this 2007 point, if you partition the air-sea regressions, you're getting a change in strength, which we find to be pretty interesting. And with that, I would like to discuss a little bit these results that we acknowledge that these results are based on a monthly mean basis, which in a sense is going to average out a lot of the underlying physical processes that might happen on sub-monthly timescales, as well as a range of spatial scales as well. You have these regions of western boundary currents, there's a lot going on. You're getting interactions happening on atmospheric frontal scales, oceanic mesoscales. But we find that with the intent of looking at broader climatic timescales, that taking a monthly average is still representing the signal well, without sort of overly averaging out the underlying physical processes. And with that, I'm thinking that I should have enough time left for questions. And if people want to continue discussion, I'm happy to.
We have plenty of time for questions to James. Please go ahead.
Great job, James. Really cool work. So there's this weird little mini western boundary current in the Indian Ocean and the Arabian Sea, which might be interesting to look at in terms of this is probably way beyond the scope of your master's thesis, but maybe Gemter. And it could interact with like monsoon stuff. And that would be really interesting to look at if that has some kind of impact going back and forth.
Yeah, I've just started to, now that we're starting to wrap up this project for my PhD dissertation, I'm starting to look at other regions as well. So I'll definitely take a look into that. Thank you. Yeah, Justin?
I had a quick question. Did you look at satellite data of precipitation?
Yeah. I think it's in, oh man, I have a lot of supplement. Okay, that's okay. Yeah, satellite data it's a little bit noisier, but it's really, the same signal is there.
Hey, nice talk. I was just wondering, why do you would expect that the signal stays in the boundary layer? So why are you surprised by your result that you have the correlation above the boundary layer, you create low-level PV in convection?
Yeah, okay. I am not a hardcore dynamicist, so I'm gonna be conservative with my answer, but a lot of the literature, including prior theory that is showing what a typical vertical motion anomaly should be to offset an underlying heating anomaly, shows that it should mostly stay within the boundary layer. That, especially in the wintertime, you end up with a capping on the boundary layer in the wintertime, and it can be really difficult to move beyond that capping. I'm happy to forward some studies to you that would give you a much more fulfilling answer.
Yeah, I assume that the theory doesn't know the strong heat flux you have on the strong SST gradients, right?
Mm-hmm.
So,
yeah, thank you.
I think we have a question online. Unfortunately, I just joined in and I don't see it anymore. If the person that asked the question is able to unmute and ask the question, please go ahead. Or you can write it again. Okay, if not, let's thank James one more time. Okay, so the next speaker is not able to present today, and we instead will move the discussion that we were supposed to have that ran into the break time right now. So let's pretend I just finished the talk, and you can now ask questions. Thank you.
ask, but then I got an answer over the break. But I'll ask anyway for the benefit of the group. If you could talk a little bit about any additional costs associated with the different coordinate systems in terms of running, and also in MOM6 versus the old version of POP.
In terms of the vertical coordinate, the out-of-the-box Z-star is 65 layers, while the high command is 75. So right there we have more layers. But if it was the same number of layers, the algorithm is slightly more expensive. I would say 5%-ish, 5 to 10%-ish more expensive than the Z-star, just because you need to do more the remapping is slightly more sophisticated. In terms of POP, I think, if I remember correctly, it's like the numbers is 4 to 5 times more expensive than POP. Yeah, people are nudging. Yeah, yeah, yeah. It's like driving a Ferrari. I'm sorry. Good point. Yeah, yeah. We were like recently, Alper added the option to do lane block elimination, so we gained 25% in costs just by doing that. So we should revisit that. So we should be slightly better now. A lot of the numbers, yeah. Right, true, yeah. Yeah, so Peter said a lot of the differences because we have high resolution with MOM6. So the MOM6, the current grid is 2.5 higher than POP. And?
Okay, so starting again, yeah, I wanted to thank everyone for all the work that's gone into this objective comparison of these two grid systems. I guess I wanted to speak again from the kind of other climates perspective, where often we don't have an a priori notion of what the stratification might be. And I guess I'm wondering if you could suggest, what do you think a good workflow is if we're trying to simulate like the Cretaceous? Should we just use the Z-star coordinate? And then by doing that, might we lose, are we kind of starting off with a model that is less tuned? And might we lose some of the comparisons that we would get to the kind of flagship CESM configuration? Yeah, because I'm just wondering if that provides another degree of ambiguity in what those climates look like, is this sort of a priori choice of these density coordinates.
Yeah, thanks for the question. We are aware of these issues, and I've been working with Jean too. So Jean is running LGM with CSM3 MOM6 Z-star, and is on my to-do list to give him a set of values for the high command coordinates so he can start doing a comparison with high command too. But to your question, what we've been talking about is this idea. So let's say you need to have an initial condition to begin with. You give us an initial condition. We can give you a set of ideal density targets that will work with that initial condition. But let's say you're doing a very long run that your TNSs will drift substantially, that after 500 years, the initial density targets no longer work. We're starting to think about a tool that OMWG will develop, and Alsor is visiting us late in the summer, and that's something that we could target for his visit, that as the model progresses, internally we can start adjusting the interfaces to always kind of maximize the resolution in density space for a given TNS. It is a research question. Nobody has done that yet. We don't have that tool, but conceptually, it's totally doable as long as we're doing frequent enough, and not after 100 years there'll be a jump. But conceptually, it's doable. So I guess one question back to you guys is, when are you planning to do such a simulation?
Yeah, it's a fair point. I mean, I guess if there is an online adaptive framework that could be really neat and potentially a solution. You know, we are planning to run these kind of, you know, Cretaceous, for instance, simulations in the next couple of years, but that's using, yeah, that'll be using CESM2. So, you know, we can, I don't want to speak for the Paleo group, but yeah, we'll start with older versions of the model first.
We can make that happen. Sure, please.
So we're absolutely committed to working with people in the short term to getting solutions. If anyone needs them in the short term. Longer term, though, we're also committed to not just taking and tuning the existing hybrid coordinate framework, but to developing and making it better so that it won't face these difficulties. And this is all, it's not just us who are interested in doing this, but other modeling centers using MOM6 across the US. So over the next, you know, up to 5 years, max, we hope to have all of these things worked out.
I just wanted to make a quick clarification on Gustavo's earlier comment about the C-grid. I actually have a run where I've turned on the C-grid and the SICE model coupled to MOM, and they're both running on the C-grid. The complication is the coupling. We don't have the coupling infrastructure to do this all on the C-grid yet. And I mean, it's a really difficult question. I'd love to have conversations about it because no matter what you do, you're interpolating. And so I'd like to understand, you know, what is the least amount of interpolation that we would need to do if we wanted to do this. So, yeah.
So you're saying we can already use the C-grid capability and therefore not worry about one point channels. Yep. Okay, well, we should start using it then, like we should start testing, but it seems like regardless, like if you do on the C grid, we still need to average because we pass properties on the A grid at the cell center to the coupler. Is that your point? Yep. So what seems like we need to allocate software engineer time to look into this. Yeah, all right, we should put that into the
The bulk formula require all of the state variables to be co-located. To compute a turbulent flux, you need the velocities and the state to be co-located. So it's inevitable. And we hear the same red herring from the earthworks folks who say we're going to run on the same grid so we don't have to do any interpolation. It's wrong. You always have to do interpolation unless you're running on an A grid.
Yeah, so now I'm unsure what do we need people's time for? Like, seems like we have all the ingredients to be running SICE on a C grid and infrastructure ready. Is that correct? Yeah, okay. All right, so I'll check that I'll make the arrow shorter and we've completed one more task. Any other questions? Justin?
A kind of devil's advocate question about mixed layer depth. And it's kind of interesting that it looks like MOM6 is too deep in the subantarctic, and I've looked a lot there, but also subpolar gyre. And that was also true with POP. Low resolution, but I just wondered about then the large-scale impacts, and it seems like the AMOC in the new simulations seem to be okay from what you're saying. And so I'm just wondering, well, we look a lot at these mixed layer depths and they're way too deep, but it seems to be okay. It's kind of strange, and I wondered if maybe the sensitivity to the Bodner parameterization, which does reduce the mixed layer depth, does that, have you seen anything else happen that's interesting from those kind of simulations? Maybe it's a bit recent to say.
Yeah, it was recent, but I would say that there were no showstoppers besides the shift in the convection in the Labrador Sea. To me, that was the only kind kind of negative outcome of turning on Bodner. Also, it goes away one of the tuning variables, which is the length scale of the front, but there are other parameters that we have to choose to make that happen. So I feel like we got rid of one parameter, but there's a handful of parameters that came in with that option, and I've been using what Kate Hadstrom recommended in our chat, MOM6 chat, and now Kate a few weeks ago just added an option to provide one of these parameters spatially variable as well. So it might be feels like this is a bit of a might be more complicated than what it looks like. We need time to digest, but the good news is the code is merged into dev and car, and it will make it through the science freeze. So we have some time to explore the Bodner et al. Options in depth. You have 5 minutes left.
Paul Hall is still online, and so maybe we could talk a little bit about waves some more. We haven't been doing a lot of work in the last few months evaluating wave options just at all. So Paul, you shouldn't feel like you're being left out with theory waves. We just haven't been doing anything, partly because some initial work suggested that the results were sensitive to the coordinate, the vertical coordinate, and so we were delaying working on waves until we had picked the vertical coordinate, but we have picked the vertical coordinate now. So we're hoping over the next few months to do more work with waves, and hopefully we can involve you with that. But I'm up here talking about this, and I have had no involvement with the wave part at all. So I don't know if anybody who's here who knows more about it would be interested in commenting.
Update on waves either, because this is mostly Bill's work, but going back to Paul's question about whether CSM 3.0 or 3.1 would be a better option for theory waves. So if your primary concern is for this theory waves to be working with CMIP 7, then 3.1 is a perfectly fine choice, because that's when we will incorporate CMIP 7 forcings. So I think we shouldn't feel pressure to add theory waves into 3.0 just to, make it work with CMIP 7. But yeah, did you have any other concerns regarding the, scheduling of?
No, not so much. And thanks for that feedback. That I know you and I had emailed back and forth about this a little bit. But if CMIP 7 if it's 3.1 is really CMIP 7, the target for CMIP 7, then 3.1 is a good target for us too, as far as we're concerned. Do we have an actual time frame for that?
Not yet, but it's really dependent on the 3.0 calendar.
Yeah.
But just to reiterate again, 3.0 is what we call the development release. The actual production release is going to be the 3.1, so that's another thing that we should keep in mind.
Okay, yeah. Great.
Thanks.
Thank you. And thanks for all your help with this, Alper.
Sure, thank you.
So we think we talked to the Ocean Model Working Group a while ago, though, and the problem with the theory waves is we lose the sea ice interaction. So do you have any ideas or thoughts there? Because I've been spending a lot of time working with WaveWatch and its billion attenuation schemes. And so I would definitely love an alternative, to interact with the sea ice. And MoMA's Pickles model has some of that, but I think, ultimately we need to have a plan in place too that we can interact with the sea ice as well. So.
Yeah, I agree on that. And I will say I don't know enough of the physics of the wave ice interaction to be able to speak to this, but perhaps MoMA can. And speak of the devil, there he is.
I can just comment again. I think that your idea of making theory waves a wave component is the right direction, because then it's easy for Pickle to sway in when it's done. It will be not for CESM 3.1, but somewhere after that, right? So, but on the short run, you might have to make the choice between an MIZ with an active waves or a low resolution wave model with then not as good Stokes drift vector. So right, there's a trade-off between low resolution wave watch with an MIZ, and then you might lose information in the resolution of your Stokes shear, or you say it doesn't matter that much and you can do that. But that's the option right now.
Okay, well, thank you everybody for the discussion. It's now 4:30 Mountain Time, and our next speaker is Andrew Kiss from Australia. Andrew, are you online?
Yep. Can you hear my audio?
Yes, we can. Please share your screen and feel free to start presenting.
Cool, thank you. All right, is that coming through okay, the slide? I can't hear anything, so I'll just proceed.
You can see fine. Yeah, you're good.
Okay, great, thanks. Yeah, so thanks for including us in this workshop. So my name's Andrew Kish. I'm working at the Australian National University, and I'm presenting on the behalf of quite a large team who are working on Australia's next ocean and also climate model suite, which and the ocean component is called Access OM3. So this is a work of a lot of the development is being done in a new facility called Access National Research Infrastructure, headed up by Andy Hogg, and also the COSMA Consortium for Ocean and Sea Ice Modelling in Australia. So just to provide context, so the Australian ocean and sea ice modelling community is quite large and active and growing. So within this community, we've got researchers across a whole range of different universities, as well as the national research bodies such as CSIRO and the Antarctic Division, and the Bureau of Meteorology, the Weather Forecasting Service. And this community has grown up around what we call Access OM2. This is a model that was released in 2019. And since then, it's underpinned about 70 or over 75 publications, and also been formed part of the Australians' climate models, which were contributed to CMIP6, and also a newer version which uses a quarter-degree ocean. And there's also a 1/10th degree version of this model, which is forming the next ocean and sea ice forecasting system for Australia. So this is just a little overview of the current workhorse. This is Access OM2, and so it's a global MOM5, CEIS5 configuration. It's available at 3 resolutions, from 1 degree through to 1/10th of a degree. The coupler is Oasis, and we force it with JRA55 DO. And so the architecture is shown there on the left, just to give you an idea of how it's all strung together. And a lot of the research work that's been done with this is focused on the Antarctic and Southern Ocean region. And it's unusual in its ability to represent Antarctic bottom water really faithfully. So this is one example of a publication that demonstrates that, showing the spreading of different source waters of Antarctic bottom water through the globe. So So the Antarctic is a particular focus, but the model has been used in studies covering all sorts of different regions and timescales and processes globally. But because it's based on MOM5 and SICE5, which are now kind of legacy code, we're wanting to upgrade the capabilities we have in Australia. So that's what I'm really talking about today. So the new ocean and sea ice model is called Access OM3, and some of the driving forces, the scientific driving forces for updating these components, are kind of shown in this schematic here. So we're interested in being able to represent flow in ice shelf cavities, which is not possible in MOM5, but possible in MOM6. We're also interested in a better representations of sea ice that are available in size 6, for example, the landfast ice, and a flow size distribution. And with the flow size distribution, we also need to include a wave model. So we'll be including WaveWatch. We are including WaveWatch 3. So this is breaking up the sea ice, and the sea ice is damping the waves, and also the waves are coupled to the ocean and affecting the surface mixing. So in order to bring this about, we've actually had to adopt an updated architecture as well. So we are using the NUOPSI coupling framework instead of OSIS, and so we've got this hub and spoke approach, and we've picked up the CMAPS mediator and driver, and are using CDEPs for the forcing components. So this is the architecture we've got. We're setting up a whole series of configurations. We already have a 1 degree version of this working, and also a 1/4 degree version running, but without WaveWatch at this stage, but that will be coming in soon. So I'll be showing some examples of this in the next few slides. And so the next steps we're working towards, so we're using the latest components of these model components, the latest versions, I should say. And so we are going to be moving towards a C grid with SICE, so a new topography, and we're also working towards higher resolution, so 1/10 degree and beyond. There's also a biogeochemical component here called Wombat, and this is the component which was in Access OM2, and it's being ported into MOM6 by Doogie Squire and upgraded to be more capable by Pierce Buchanan, and Doogie will be talking about this in the talk after this one. And there's some interesting technological things there to do with using generic traces for that. Now, we're also wanting this ocean sea ice wave or ocean and sea ice component to be part of the next generation climate model, and that is called Access CM3 and the Earth System model ESM3. And so this is what we're aiming at with that. And so we're not using WaveWatch. We're not intending to use WaveWatch at this stage for the climate model, but at some point in the future, it may be something we can start using. And the big sticking point here is that, as in our previous climate model, we're using the UK Met Office's unified model, and that doesn't come with a NUOPSI, or didn't come with a NUOPSI cap. So some of the development work we've been doing here has actually made a cap. So now the UK UM is now a NUOPSI compatible component. We've got a test configuration running at 1 degree, and it's run for a decade or so. It's the performance is actually quite good, and the sea ice cycle looks pretty realistic. That there's a bit of tuning to be done, and we're currently using the UK's Joules land surface model, but we're intending to move to an upgraded version of the Australian cable land surface, and so for the Earth System version of this, we'll also be using Wombat, but that's still over the horizon at this stage. So this is intended for CMIP 7, in which we'll have a 1/4 degree ocean in an N96 atmosphere. So just to give an idea of how we're coordinating our development, this is showing in the green lines basically different model configuration versions, And so there are MOM6 SI6 versions, there's MOM6 SI6 WaveWatch versions, and there's also a coupled model and an Earth system model. And so this is the Access OM3 suite, which we're going to be producing configurations of in multiple resolutions with ocean and waves and sea ice. There's also a version that drops the waves, and that version will be fed into the climate model, which will be being developed at these two different resolutions of 1 degree and a quarter degree, and including as an Earth system model. So this is the ambition. We'll see how close to this we can get for CMIP 7, but long term, this is where we're headed. And another part of the infrastructure we've put in place here is to facilitate very easy upgrades to our model components to use the state-of-the-art that's coming out internationally. So all of the black arrows here are basically pull requests and upgrades to the components. And so we're already using the latest versions of MOM6 and SI6 and WaveWatch, and we're regularly upgrading those as we go. So not only does this give us the advantage of all the great development work that's being done, it also puts us in a position to contribute much more meaningfully to the current state of the art, and we've been doing that recently, and we'll be continuing to do more of that as time goes on. So I'll just show you some preliminary results we've got from our MOM6 SI6 WaveWatch 3 simulation. This chart at the bottom is just showing the things that are being coupled between those model components. So we've got two-way wave ice and wave ocean interaction working on a technical level, but we're working to basically improve this with some tuning and trying out different schemes. So we've investigated a few different WaveWatch wave attenuation models, so viscoelastic and empirical schemes, and we're intending to move towards the most recent Malin et al. Model and try that one out. So I'll just show you some examples of that. So this is with the damping of the sea ice by viscoelastic representation, damping of the waves by a viscoelastic representation of the sea ice in WaveWatch. So the top left is showing the surface waves, and this is on a log scale, and you can see all this white stuff going on in the Arctic sea ice, and this is actually where it has gone down to zero in single precision output. So we're getting NANs in the log scale. But there's a green line there, which might be a bit hard to see, which is the 15% sea ice concentration. And the waves are penetrating a little way into that, but not as far as they should. And so one of the things we're trying to investigate is how to improve that wave penetration into the sea ice. In the top right, there's an animation of the generation of the evolution of the mean sea ice distribution, flow size distribution, as a result of wave breakup. So another example is a test run now changing to a different empirical damping scheme, and this is actually working worse. So we're looking at different versions as well. But in this case, the waves are damped even more strongly, and as a result, the ice builds up in the largest flow size category. So basically all of the ice ends up in the largest flow size. So this is not what we want to be happening, and this is just an example of some of the work to date in attempting to get to grips with how the wave model, the wave representation of sea ice interacts with the sea ice and the waves in this coupled system. So we're collaborating and looking to collaborate more closely with people who are working on these problems. I'll switch gears a bit now just to show you some things that may be of interest that we've been working on in the COSM consortium on regional models. And so MOM6 has some nice regional modeling capabilities, and it has nice handling of the boundary conditions and the vertical interpolation and so forth. So we've been working on circumpolar Antarctic models and also other regional models in different locations, including nested versions. And for these, we use our 1/10 degree Access OM2 output to drive MOM6 SIS2 at the boundary. And in this nested configuration I'm showing in the middle, we've got MOM6 nested within MOM6 to drive the boundaries. So just a couple of examples of that. This is our Pan-Antarctic regional model. So it's circumpolar and it runs from the Antarctica up to 37 degrees south. And we've stretched it all the way to 37 south because we are not handling sea ice open boundary conditions, only ocean open boundaries. So we have to be completely ice-free at the open boundary. And we've got configurations running at 1/10th, 1/20th, and 1/40th degree resolution over this quite large domain using Z-star, but we've done a few explorations of other coordinates. And yeah, with runs that over a decade in length. Now, as we've explored different regional models, we've actually also developed a toolkit, a Python package, which makes it much easier to generate new regional models in any region of the globe you like. So basically, you specify the box that the regional model is going to be in, and this Python package will set up the entire experiment. It will set up the grid for you at whatever resolution you like, set up the surface and boundary conditions, the initial conditions, bathymetry and tidal forcing. So this is developed by Ashley Barnes, who's completing his PhD in our group. And there's a paper in review at Journal of Open Source Software, and it's available on GitHub if you want to give it a go, try it out if that's of interest to you. So an example of configuration done with that is this Tasman Sea region between Australia and New Zealand. You can see as this spins up, the initial 1/10th degree initial condition is evolving into much higher resolution features because the model grid in this case is 1/80th of a degree. And this is actually for an investigation of the impact of tides on and by ocean eddies, internal tides, I should say. And so the flickering you can see in this animation is actually the tides which are being imposed both as a body force and through the boundaries. So that's just one example. There's been a number of different regional models set up with this tool. So I'll just leave it there. This is basically a whirlwind tour, an overview of what's going on in Australia at the moment. We've got quite a large group of people working on ocean, sea ice, biogeochemistry, wave and climate modeling. We're moving towards this new MOM6, CESM and WaveWatch 3 based models. We've adopted CSM components, and with NUOPSI, we've got NUOPSI working with the UK Met Office, and we're looking forward to closer collaboration. We're now a member of the CEIS consortium, and we'll shortly also have a MOM6 development nodes. So we'll be testing MOM6 against our own configurations. And finally, there's a regional configuration tool for those who are interested in that. So thank you. I'll leave it there and take questions.
Thank you very much, Andrew. We have time for one quick question. Frank?
Andrew, I'm wondering, across your resolution hierarchy, either in the global model, these regional models, are you using or aspiring to use scale adaptive, scale aware lateral closures, or are you considering each independently and choosing closures as appropriate to that resolution?
We'll probably be doing something quite similar to what we did with OM2, which was to use different closures at different resolutions. Yeah, so we had GM at the 1 degree and turned it off at 1/4 and a 1/10th degree, for example. Yeah.
Thank you. Our last speaker is Dougal Squire. Please go ahead and share your screen.
Thank you. Hopefully you are seeing my slides. If not, please yell out.
Yes, we are.
Yeah, hello everyone. My name's Dougal, or Doogie. I'm a research software engineer at XSNRI, which, as Andrew just explained briefly, is a relatively new organisation that's been set up in Australia to support and develop our climate modeling capabilities. And I sit in the Ocean Sea Ice Model Development team, where I'm currently helping to develop CESM3, which again Andrew just spoke briefly about. And I'm going to provide a little bit more detail in my talk about on the Ocean BGC side of CESM3 and XS models. So first, a little bit of background. This is a wombat. They're a very cute marsupial that can be found all over Southeast Australia. And this is also a wombat. So wombat is the name of Australia's community ocean biogeochemistry model. It stands for Whole Ocean Model of Biogeochemistry and Trophic Dynamics. And it's mostly been developed by Richard Mateer and Matt Chamberlain at CSIRO over a number of years. And it's the ocean BGC model that was used in Australia's CMIP6 contributions. So if you're familiar with CESM 1.5, it's the ocean BGC model that was used in that Earth system model. And in that form, which is the form that's shown here, it's a pretty simple NPZD-based BGC model with the additions of bioavailable ion limitation, DIC, calcium carbonate, alkalinity, and oxygen. However, there's work underway that I'll talk about towards the end of this talk to improve, add complexity, bring wombat up to the latest science. That's being led by Pierce Buchanan at CSIRO. So as Andrew said, we're currently developing our CMIP7 era access models. Access is sort of the catch-all name for the Australian climate modelling suite. And that's involving a lot of changes relative to our CMIP6 era models, which are the ones that are currently being used by our research community. So of particular relevance to this talk, as Andrew said, we're moving away from the OSS MCT coupler. We're now using new OPSI and CMIPS, and actually the CESM CMIPS driver at the moment. And we've upgraded our ocean from MOM5 to MOM6. So ignoring the model configurations with an active atmosphere, you can see there are lots of similarities with what's available and used in CESM. And actually, we're heavily leveraging a lot of the work done by the CESM community and developers. So thanks very much. In our CMIP6 era models, Wombat, our BGC model, is implemented directly as a tracer package in MOM5. And we've actually ended up with multiple Wombat code bases for our different access models, which is obviously problematic from a maintenance and development standpoint. And that MOM5 version of Wombat can't be used as is in MOM6. So we've taken the opportunity with the development of our CMIP7 models to redesign Wombat so that a single code base can be used across our CMIP7 and CMIP6 era access models. And so that, of course, means that any upcoming science developments that I'll talk about can be utilized in both if and where we want to. So to do this, we've re-implemented Wombat using what's known amongst the GFDL models as a generic tracer, or using the generic tracer API. This API is generic in the sense that it can be used by different GFDL ocean models. So, for example, there are interfaces to generic tracers in both MOM5 and MOM6. And this has a number of positives. Firstly, it's modular, as I said, so we can use the same Wombat code in different access models, even access models that use different versions of MOM. Relatedly, it's been really useful from a testing perspective. So although the main motivation for the rewrite was to get Wombat running with MOM6, it's actually been very handy to be able to compare outputs from the original and generic versions of Wombat using MOM5. And that's revealed a couple of issues that we're resolving. Another big positive is there's a whole suite of other BGC models that are implemented via the generic tracer API. So for example, Cobalt, Topaz, and Bling use that same framework. And these can be turned on and off and configured at runtime in a very similar way to each other. And that ability to use and compare different ocean BGC models in Access is something that our community flagged as being quite important to them. The catch is that the generic tracer code base is written under the assumption that you're using GFDL's coupler, which is called FMS coupler, and we're not using that. As I said, the CMIP6 era access models use Oasis MCT, and the CMIP7 era models use NuOpsy. And the specific issue there is that the generic tracer code base uses a particular type of data structure to handle the surface tracer fluxes that's pretty specifically designed for use with the FMS coupler. And so any generic tracer module that requires external coupling uses these data structures, and that's basically all of the generic tracer BGC models. So the way things work in FMS coupler is that there are 3 coupler data structures that are carried by the coupler, and these contain basically all of the information needed to calculate those tracer fluxes as well as the tracer fluxes themselves. So there's one structure for the atmospheric fields and related parameters, one for the ocean fields and related parameters, and one for the actual fluxes that get calculated from the atmosphere and ocean fields. So by way of example, imagine that you have a generic tracer module that requires air-sea gas exchange of CO2, and you want to calculate that CO2 flux using OCMIP2 calculation protocol. In this case, your initialized coupler data structure should contain a field for that CO2 flux. Here I've called that CO2 underscore flux. And that allocates space for the various arrays and parameters that are involved in that flux calculation. So within one coupling loop with the FMS coupler, the atmospheric tracer concentration, wind speed, surface pressure, all of the atmospheric fields will be updated from the atmospheric model. The flux arrays, so over on the right-hand side, surface tracer flux, piston velocity, delta pressure, will be calculated from the atmospheric fields and from the ocean fields that were set at the previous time step. And then the ocean model will take those fluxes and the ocean fields, pass them on to the generic tracer module that you're using with those updated tracer concentrations, accounting for those surface fluxes, and then update the arrays in the ocean fields. And so importantly, the initialization of these structures and the actual calculation of the fluxes themselves are done inside the FMS coupler. And that prevents or has prevented running MOM6 with generic tracers with any other coupler. And so to get around this, we've made modifications to the MOM6 NuOpsy cap. So that's the interface layer that sits between the coupler and MOM. And those changes basically do 3 things. They initialize the FMS data structures with the fields and arrays that are required by whatever generic tracer module is configured for use. They then populate the atmospheric fields from arrays that have been received from the coupler. And then within the cap itself, they calculate the tracer fluxes to be used by the generic tracer module. The reason I'm kind of saying all this is because this NuOpsy cap is the same code that's used by CESM and MOM6. So if there is interest from the CESM community in running with Wombat or Cobalt or these other generic tracers, these changes maybe provide an example or a starting point to enable that. There are a few outstanding issues. The first is that the generic tracer API, in being generic, is also somewhat restrictive. So for example, there's no obvious way to apply virtual flux corrections if you're doing salinity restoring for via a salt flux, for example, which we do in our ocean models. The second kind of similar issue that we're encountering is that the FMS coupler data structures are restrictive in terms of what types of fluxes they can handle. So for example, we'd like to couple sea ice BGC in Wombat, and there's no obvious way to do that at the moment with the FMS coupler types. So in addition to getting those issues resolved, there are a few developments in Wombat that are planned and actually underway. These are being led, as Andrew said, by Pierce Buchanan at CSIRO. And so moving forward, we're going to move forward with multiple versions of Wombat with varying levels of complexity. We're maintaining a version of Wombat that's a similar level of complexity to the CMIP6 era Wombat that I described right at the start of this talk. So that's really a a lightweight version that's useful for runs with large ensembles or very long runs. Sorry. That version is getting rechristened as Wombat Lite, and it has some improvements, including an updated RGB light scheme, so where phytoplankton interact with light based on the absorption spectrum of their pigments, an updated ion cycle that includes ligand-bound and free ion, explicit chlorophyll to carbon and ion to carbon ratios within the phytoplankton cell, allometric scaling for nutrient affinity and detrital sinking, and permanent burial, which wasn't in the previous iteration of Wombat. And those changes have helped to improve some of the deficiencies that existed in our CMIP 6 era Wombat. So these are plots created by Pierce, which show Wombat with and without his developments, and compare those to observations in the top row. And so the first column shows DJF CO2 flux, where we can see improvements in the Southern Ocean ingassing, as well as outgassing in the subantarctic Pacific and North Atlantic. In the middle column, that shows annual mean integrated net primary productivity, where I think Pierre said that the updated model has about 15 additional petagrams of carbon per year. And so that brings us at least closer to what we might expect globally at this model resolution, given the observations we have. And then on the far right is annual mean dissolved iron at the surface, and that shows some clear improvements with Pierce's updates. So Pierce is also working on a new Wombat Mid version. He's chosen to go with beer-inspired versioning naming. And that includes multiple phytoplankton, zooplankton, and detrital sinking groups, active nitrogen and silicon cycles, and updated grazing formulations. He actually also has plans for a Wombat Full, which will be more complex again, but I don't think they're bedded down enough to say much more about them at this point. So that's all from me. My main points are that we've re-implemented our Ocean BGC model as a GFDL generic tracer to let us use it across our access models across MOM5 and MOM6. We have a working example of using those generic tracers with couplers other than the FMS coupler in MOM, and improved versions of Wombat hopefully coming soon. Thanks.
Thank you very much, Dougie. Before I open for questions, I just want to thank one more time Dougie and Andrew for waking up early and coming to share your progress with us. And I would like to offer, when you host a equivalent of the CSM workshop, please reach out to us. I'm happy. Some of us will be happy to stay awake until later and give a talk on your workshop. And looking forward to continuing this collaboration in the future. All right, questions for Dougie?
I have a more general question, maybe even to the speaker before. So you use WaveWatch for size, but do you use it for any other coupling with the atmosphere and ocean, or is it just there to make waves in the MIZ?
Most of the investigation we've done to date has been in the coupling with sea ice, but it is also coupled to the ocean. So yes, but the Access OM3 is driven by a prescribed atmosphere. So there's it's not interacting with the atmosphere.
Alistair?
Hi, Dougie. Sorry. I was thinking about this issue of the gotchas with the FMS coupler. Those types reach all the way down, from the coupler all the way down to your tracer code. I was just wondering, does that suggest if we had swapped in your diagram, you had Wombat within MOM6? We've always done the biogeochemistry as tracers vectored by the model, but if you had Wombat as the interface from Nuopsy, and then use MOM6 called from within Wombat, providing the service of vectoring the tracers, then you would be able to basically make MOM6 independent of those fluxes. I was wondering if you could turn it around. I'm not suggesting you should redesign, but it just suddenly occurred to me. We've had this problem, and I hadn't realized that. I mean, we've always struggled with how to compile a model without traces from FMS because they reach all the way through the code. And so anyway, I mean, it's a small rearrangement of APIs, but just make Wombat appear as an ocean model with all its fluxes coming in from NOPSI, and then it doesn't matter. It's just turning things around. Something to think about.
Yeah. I need to think about that, I think. I'm not sure I fully understand what you're suggesting. It maybe sounds similar to what the way that things are done with Marble, but I could be misunderstanding. No? See you shaking your head. I think I need to think about that.
We'll come back.
I think we're ready to wrap up. Please go check the posters after here. And I would like to thank all the speakers one more time.